GCE Advanced Level Chemistry Practical Series, Experiment number 31. Experimental determination of the effect of concentration on the rate of reaction between sodium thiosulfate and nitric acid. Let's take a look at the aims of this experiment. The aims of this experiment is to investigate the effect of concentration of reactants on the rate of reaction and to determine the order of the reaction and write the rate equation for the reaction. So in this particular experiment, we are going to see how concentration of each reactant is going to affect the rate of the reaction, or how fast the reaction takes place. And then using the findings of this experiment, we can calculate the order of reaction with respect to each reactant, and then we can write the rate equation using the information we find here in this experiment. So now let's move on to the next slide. Let's take a look at the introduction to this experiment. The initial rate of a reaction is a measure of the time it takes for a minute amount of change to occur at the onset of the reaction. If the reaction rate is denoted R, R is equal to amount of change divided by time. Now students, we know rate of a reaction is measured in this particular manner. Rate of a reaction is equal to the rate of amount of change divided by the time it took for that change to occur. So rate is equal to the amount of change divided by the time it took for that change to occur. So now if you take a reaction, if you allow the reaction to go to completion, from, let's say, we start the reaction by mixing two reactants and we know their initial concentrations, and we allow the reaction to take place to completion, and we measure how long it took for the reaction to go to completion. Let's say it took about 10 minutes, right? And then afterwards, students, we can consider for this entire reaction to take place, for the concentration of the reactants to go from their initial concentration to 0, this particular amount of time was spent. So we know the amount of change that took place. Initial reactant concentrations went all the way to 0. So that means we do know the amount of change that took place, and we do know the time it took for the reaction to take place. So if you measure the rate in the manner that I just explained, that will be an average rate for the overall reaction. Because as we know, there are certain reactions that are influenced by the concentration of reactants. So in the beginning, where the concentration of the reactants are really high, when there is a higher concentration of reactants, you will have a higher rate. And then as the reaction proceeds, what happens? The reactant concentrations are going to go down. So as the reactant concentrations go down, the rate of the reaction will also slow down. So at the beginning, the reaction rate was high because there was a higher concentration of reactants. But at the middle of the reaction, the reactant concentrations are low. So the rate of the reaction will be low. And towards the end, it will be extremely low. So if you allow the reaction to go to completion and then measure the rate of the reaction with the data that you have collected, at that point you get an average rate. So using that sort of rate is not going to be ideal for a reaction like this. We do use a different type of rate referred to as the initial rate. So to measure the initial rate, students, what we do is we start the reaction with known concentration of the reactants, and we allow only a very small change to take place. Only a very small decrease of the concentrations of the reactants will take place. So we say we allow only a minute amount of change to occur, and we measure the time that it takes for this small change to occur, and then we know the amount of change that happened and we know the time it took. So if you take the amount of change and divide by time, we get the rate at the onset or at the beginning of the reaction. So at the beginning of the reaction, we know the concentrations of the reactants as well. So we say this particular rate is associated with the initial concentrations of the reactants. So that is why we call this the initial rate method. When you are starting the reaction, what is the rate of the reaction? If you wait for the entire reaction to take place and then measure the rate, that would be an average rate. As you know, in the beginning of the reaction, the rate would be higher. And then as the reaction proceeds, the rate will slowly go down. Right? So therefore, if you take the overall reaction, and if you know the amount of change that took place and the time that it took for that particular change to take place, then what you get when you use those data and calculate the rate is going to be average rate. And we do not want average rate because, as the name suggests, it is not going to communicate to us the rate at a specific concentration of the reactants. So when we are talking about initial rate here, what we are doing is we take the reactants with known concentrations and we mix them. We know their initial concentration in the reaction mixture, and then we allow only a minute change to take place, and we measure the time it took for a constant amount of minute change to happen, and then we use this equation to get to the initial rate. So students, after finding the initial rate, we can proceed with the rest of the experiment here. So keep in mind, in this experiment, we always measure the initial rate. We don't do the reaction for very long periods of time. Time frames are majority of the time less than a minute. So the amount of change that has taken place in the reaction mixture is small. So therefore, we can say that the initial concentration of the reactants produced this specific rate of the reaction. As demonstrated earlier, we can determine the initial reaction rate. The rate observed at this stage represent the reaction rate when the concentration of reactants are identical to their initial concentrations at the outset. When assessing the initial rate, it is essential to minimize the change in concentration. This is crucial because minimal change in concentration allows us to treat the concentration as equivalent to the initial concentration. Consequently, we can express the reaction rate as the rate observed at the initial concentration values employed. So what this paragraph talks to us about is, as we know, when the reaction takes place, the reactant concentrations are always going down. As the reactants come together to form products, the reactant molecules will decrease, so therefore their concentrations will come down. However, when we are measuring this rate that we have mentioned here, the initial reaction rate, we are trying to measure a very small amount of product that is produced, or very small amount of reactants that are reacted will be taken into account. We can measure the rate by taking amount of change divided by time. So amount of change could be amount of product that is produced or amount of reactants that are used up. So over here, we are actually measuring, in this particular experiment, we are measuring a certain amount of product that is produced. But we are measuring only a very small amount of product. That means the amount of reactants that are used up are also quite small. So after the reactants are used up, the concentration, or after a very small amount of reactants are used up, the concentration of the reactants are not very different to the initial concentration, because we only used a minute amount of reactants. Minute means a very small amount of reactants. So therefore, the initial reactant concentrations and the reactant concentration after a very small amount of reactants have gotten used up is more or less identical. So students, we can say at the initial concentration of the reactants, the rate observed is known as the initial rate of reaction. Equation of the reaction between sodium thiosulfate and nitric acid. Sodium thiosulfate and nitric acid react together will form sodium nitrate, sulfur solid, sulfur dioxide, and water. Sulfur dioxide will also be produced as a gas, and some of the gas will be dissolved in water to produce SO2 aqueous. So students, sulfur dioxide's pungent smell will be observed when you are carrying out this experiment. Now, apart from that, one of the most important products here is this solid sulfur that we have produced here. Now, solid sulfur in this particular reaction will be produced as fine particles of sulfur. So, this solid sulfur precipitate will be produced as very fine, very small particles of sulfur. These fine particles of sulfur is going to be distributed throughout the aqueous medium and will produce a colloid. Or one of the observations you are going to make is that when very small sulfur particles are distributed throughout this aqueous medium, the aqueous medium will appear milky in nature. We say the reaction mixture turns milky. So this milky appearance is there due to these sulfur particles being produced throughout this aqueous medium. And this solution also is referred to as milk of sulfur. Although we say the appearance is milky, there is a slight yellowish color to this appearance. So students, this particular sulfur that is produced here is also referred to as colloidal sulfur as well. So one of the reasons why we call it colloidal sulfur is because the particle size of this solid sulfur that is formed here is quite small. When they get distributed throughout this aqueous medium, it produces a colloid. And will turn this aqueous medium milky with a yellowish color to it. Now, when we are carrying out this reaction, students, we mix two reactants, sodium thiosulfate and nitric acid. And as you know, when you're writing the rate expression, we have to have two orders for this particular reaction, because there are two reactants over here. We know we can express an order of the reaction with respect to each of these reactants. So the order of the reaction with respect to sodium thiosulfate is M, and the order of the reaction with respect to nitric acid is considered to be N. So we have two orders written over here. Order of the reaction with respect to sodium thiosulfate is M, and order of the reaction with respect to nitric acid is N. Instead of using nitric acid, we can also use HCl or sulfuric acid as well. Over here, students, instead of HNO3, nitric acid, instead of nitric acid, we can use sulfuric acid or HCl. Now, when you're taking a look at the reaction between sodium thiosulfate and HCl, we can see when you react these two reactants together, you produce sodium chloride, again solid sulfur, sulfur dioxide, and water. Sodium chloride, solid sulfur, sulfur dioxide, and water. So in this particular reaction, also you observe the formation of this solid sulfur precipitate, and it is going to be produced in the previous example we looked at. It is going to be produced as a very fine sulfur precipitate, and this fine sulfur precipitate will get distributed throughout this aqueous medium to produce a milky appearance in the mixture. So that is what is shown over here, students. So when you are carrying out this reaction, sulfur precipitate will be produced here, as well. And over here, when you are carrying out the same reaction with sodium thiosulfate and sulfuric acid, only difference that you observe here is the formation of sodium sulfate. Other than that, solid sulfur, sulfur dioxide and water will also be produced. Other than that, solid sulfur, sulfur dioxide and water will be produced. So only different product compared to when nitric acid or compared to when hydrochloric acid is used is going to be seen over here. When you use sulfuric acid, you produce sodium sulfate. When you use hydrochloric acid, you produce sodium chloride. When you use nitric acid, you produce sodium nitrate. Other than that, the rest of the products are going to be the same. Now, after observing that, we can move on to this diagram that is over here. You can see, like in the previous instances, when you are carrying out this reaction, you produce this yellowish solid in the reaction mixture, and that is going to be our sulfur, also referred to as colloidal sulfur. So this solution will also turn milky when you are carrying out this reaction. And actually this solution turning milky is one of the most important aspects of this reaction when measuring our rate of the reaction. You will see how this is important in a second. Experimental determination of the effect of concentration on reaction rate. So again, we are reminding you the main idea behind this experiment. So when you are taking this particular reaction into consideration, where nitric acid is added with sodium thiosulfate, one of the main products that we are interested in is this solid sulfur that is produced, because we will be able to measure the production of a constant amount of solid sulfur. So while keeping that piece of information in mind, we'll take a look at the rate equation that can be written here. R signifies the rate of the reaction. Rate of the reaction is equal to K multiplied by the concentration of sodium thiosulfate into the power of its order, or M, and HNO3 into the power, or concentration of HNO3 into the power of its order. So keep in mind, the K here is our rate constant. K here is the rate constant. The aim of this experiment is to determine the values of M and N. To accomplish this objective, the time needed to produce a constant quantity of sulfur in the reaction can be effectively minimized. Consequently, the rate of solid sulfur formation can be regarded as the rate of the reaction. So students, as I mentioned earlier, we are trying to measure the initial rate. In this particular experiment, we are trying to measure the initial rate. So that means we are trying to take as much of a small change of this reaction as possible when you are trying to measure the rate of the reaction. So when you are measuring the rate of the reaction, you need to have amount of change divided by time. So we need to have as small of a change in the concentration of the reactants, or a very small amount of products formed in order to measure the initial rate. So in this case, we are going to measure a constant amount of sulfur that is being produced, and we are going to keep that to a minimal amount. We are going to measure how long of a time it takes for each reaction mixture to produce a minimal amount, a constant amount of sulfur to be produced, right? So based on, while keeping the amount of product that is produced a constant, we are trying to measure the time it takes for each reaction mixture to produce the same amount of sulfur, or same amount of the product sulfur. So at that point, we can measure the initial rate for each reaction mixture. And when you're carrying out this reaction, we'll need these equipment that I mentioned here: beaker, white paper marked with X in black and stopwatch. So this is going to be our reaction setup. I'll get to that in a second. Determining the reaction order with respect to sodium thiosulfate, or when you're trying to find M, involves positioning a clean glass beaker on an X-marked white paper, followed by addition of sodium thiosulfate and water, subsequently adding a specific volume of nitric acid all at once, while maintaining consistent eye level above the beaker. Time taken for the precipitate to cover the X mark is measured using a stopwatch. So students, over here you can observe that we have placed a beaker on a piece of paper that is marked with a black color X. So the top wave would appear this way. You have the piece of paper here, and this is the beaker, right? And we can see that the beaker has been placed on top of our X mark, right? And then to that beaker, now this is the top wave that I'm showing over here. This is the top wave, and to that beaker we are going to add our sodium thiosulfate. And first we add our sodium thiosulfate, and then we will add our nitric acid. And as we add the nitric acid, we will start the stopwatch. And as we watch this beaker from the top, while maintaining our eye level in the same position, you shouldn't be moving your head around when you are looking at the beaker. You will look at the beaker while maintaining our position. You will observe that little by little, as the sulfur precipitate gets formed, that this X is starting to become unclear to you. The precipitate that is formed is going to obstruct your wave of the X mark. So at one point, the precipitate will completely block your X mark, and you will not be able to see it. And the initial moment that this happens, where you can't see the X mark anymore, you will quickly stop the stopwatch and you will observe the time it takes for that observation to take place. Now, when we are carrying out this experiment in the lab, we will be using a camera in a fixed position, so this couldn't be more accurate. So you will be able to observe how the color of the reaction mixture start to turn into a milky color, and little by little you will observe that the X mark at the bottom is starting to disappear, and at one point you will no longer be able to see it. It will completely disappear, and at that point you will stop the stopwatch and observe how long it took for that observation to come about. So this is how you will be observing it. Although we have used a very bright yellow color, the actual precipitate will not appear a bright yellow color, students. It is mainly going to be appearing a milky color with a little bit of a yellowish hint to it. To experimentally assess how the concentration of sodium thiosulfate influences the reaction rate, a series of tests were conducted by varying the concentration of sodium thiosulfate while maintaining a constant concentration of the aqueous acid. The table below represents the test conditions and the corresponding time taken for specific amounts of sulfur to form. So students, when we are carrying out this reaction, we need to find the order of the reaction with respect to each reactant. There are two reactants. So when you try to find out the order of the reaction with respect to sodium thiosulfate, we keep all of the other conditions a constant, even conditions including temperature, right, pressure. We keep them a constant as much as possible. And apart from that, we have to keep the concentration of the other reactant constant as well. So that is also another condition. So we have to make sure that the nitric acid concentration within the reaction mixture remains or in the initial reaction mixture is a constant. So we only change the sodium thiosulfate concentration in this part of our experiment. So you can see, and now this table gives us an idea about 5 different tests that we can conduct to measure a constant amount or measure the time for a constant amount of sulfur to be formed. So how did we form a constant amount of sulfur? We mix the two reactants, sodium thiosulfate and nitric acid, and we keep observing until the X at the bottom of the beaker completely disappears. So the premise here is that to make the X at the bottom completely disappear, a constant amount of sulfur solid should be formed. At that point only, you will be able to no longer see the X produced or X mark that is at the bottom of the beaker. When a constant amount of sulfur is formed in the reaction mixture, they will obstruct your weave of the X mark that is placed at the bottom of the beaker. Right? So when the sulfur that is produced is less, you will still be able to see the X. But when you have a constant amount, or when you have produced a specific amount of sulfur, that will obstruct your view completely and you will no longer be able to see the X. So that visual observation is going to be our measure for formation of a constant amount of sulfur product. So over here you can see we will be adding different amounts of sodium thiosulfate starting from 25 milliliters, 20, 15, 10 and 5. However, now you can see very clearly we are decreasing the amount of sodium thiosulfate we are using. However, we are going to keep the amount of nitric acid that we are using a constant, right? We are going to be using the same solution of nitric acid and we are going to be using the same volume of nitric acid as well. So when you are decreasing the amount of or volume of sodium thiosulfate that we are using, the overall volume of the reaction mixture is going to change. However, we need to have an overall constant volume of the reaction mixture. To make sure the reaction mixture always has a constant volume, we will be adding water. Right? So each of these reaction mixtures have 30 milliliters of water. You can see over here 25 plus 5 and water added is 0. That means 30 milliliters is there in the overall reaction mixture. Over here also you can see the overall reaction mixture is 30 milliliters. You can see in all of these reaction mixtures the overall volume is a constant. And as soon as you mix the two reactants together, right, first of all what you do is, students, you will normally have sodium thiosulfate and the relevant amount of water in the beaker, and the beaker will be placed on top of the X mark, and then only you will be adding the nitric acid. And as you add the nitric acid, you will quickly and swiftly add the nitric acid, and as soon as you add it, you start the stopwatch. Or if you can do it simultaneously, you will start the stopwatch as you add the nitric acid. So then you measure the time it took for the observation that we were talking about earlier to appear. And you can see when we keep decreasing the amount of sodium thiosulfate used, the time taken for the same observation to appear has increased. Now these are some example data or data that is given for you to explain this theory. So you can see when you add nitric acid and then start the stopwatch, you will see the X mark completely disappearing at a specific time, and you measure that time and you have taken that time down here. And you will see when you keep decreasing the amount or the volume of sulfuric acid, or not sulfuric, sodium thiosulfate added here, you see the time taken for the same observation to come about has increased. That means when you are decreasing the concentration of sodium thiosulfate, the time it took for a constant amount of sulfur to be produced increased. So what can you say about the rate of the reaction here? When the sodium thiosulfate concentration goes down, rate of the reaction also has gone down, right? That is why the time it took for a specific amount of sulfur to be produced increased when we decrease the concentration of sodium thiosulfate. Perform the tests indicated by the test numbers 1, 2, 3 and 5, measuring the time it takes for the mark to disappear in each case. Record the observation and utilize the obtained data for further analysis of the reaction rate with respect to weighting sodium thiosulfate concentration. Ensure the beaker is well cleaned and used for each experiment. Consistently use a beaker with an identical cross section and mark for every test. Additionally, designate a single person to record each reading for uniformity and precision. Now students, when you are carrying out this experiment, if you can use the same beaker, you should be resorting to that option. However, when you're using the same beaker, make sure to clean the internal walls of the beaker really well, because the sulfur precipitate that is formed, some of the precipitate can cling to the walls of the beaker. Now, if it is not thoroughly clean, this can interfere with your observations because some of the precipitate can come into the medium. So you don't want that. You want to make sure that the internal walls, especially the bottom of the beaker, is thoroughly cleaned. And after it is thoroughly cleaned, you can use it again for the next experiment. There are 5 tests that you need to do. So after each test, you need to make sure that the beaker is thoroughly cleaned. And students, after thoroughly cleaning the beaker, or if you are using a different beaker for that matter, make sure the cross-sectional area of each beaker is the same. Otherwise, if one beaker is small and another beaker is large, for example, if you take one beaker, 50 milliliter beaker, and another, let's say 250 milliliter beaker. In the lab, you might have seen 250 milliliter beakers are quite large in diameter. So this particular difference will cause a lot of sulfur to be formed before it completely covers the X mark at the bottom of the beaker. Right, students? So when you place the beaker on top of the X mark, and when you're trying to see how long it takes for the X mark to completely disappear, a certain amount of sulfur should be produced before the X mark disappears. But if the diameter of the beaker is large, then sulfur that is produced is going to be spread even more. So at that point, the same amount of sulfur that was able to cover the X mark earlier will not be able to cover the X mark because that sulfur is now spread in a larger area. So there should be more and more sulfur produced before covering the entire X mark. So students, this particular experiment, when you are carrying it out, you have to pay attention to those details, and apart from that, to keep everything more accurate and precise, we have to use the same person to take the readings, right? Sometimes where you position yourself when you're observing the beaker might differ. Based on that, the time that you think it took for the X to disappear and the time that another person thinks it took for the X to disappear might vary based on the angle that they keep their head at, or based on how closely they observe the reaction mixture. All of these things will matter. So therefore, you have to designate a single person to always observe the X mark at the bottom of the beaker. Right. The reaction rate as the concentration of nitric acid is maintained can be written in the following way, right? So when concentration of nitric acid is a constant, we can write rate is equal to rate constant multiplied by sodium thiosulfate concentration to the power m. We have not written the concentration of nitric acid because throughout the 5 tests we keep it a constant. So R is equal to amount of change divided by time. The amount of change considered here is to make a certain amount of sulfur. So the amount of change is a constant. So we make sure that in each of these tests, the amount of sulfur that is produced is the same, right? If you use the same beaker and if you use the same X mark, and the time that it takes for the X mark to completely be covered is the time that the same amount of sulfur got produced, or time it took for the same amount of sulfur to get produced. Because if you use the same beaker and the same X mark, to cover the X mark completely, you will have to produce a very specific amount of sulfur, right? So over here, in each of these tests, we are observing how long it takes for the X to completely disappear. That means we are measuring how long it took for a very specific amount of sulfur to be produced. So since the amount of sulfur that is produced is the same in each of these tests, we can say the amount of change over here is a constant, right? Very specific amount of sulfur. You can say that it is a constant. Only thing that changed here is in each test we kept changing the concentration of sodium thiosulfate. So therefore the reaction slowed down and the time it took for the observation to appear increased. So only thing that is going to change here is time. So we can write rate is equal to K2, which is a constant, which is the same amount of sulfur, or the observation here, or the specific amount of sulfur. So now since we know it is a constant, we can write it is K2 divided by time. So we know when it comes to rate equation was rate constant multiplied by sodium thiosulfate concentration to the power m. And we know rate can also be written as rate equals amount of change divided by time. Since the amount of change was a constant, we gave it a value K2 divided by time. So at that point we can write concentration of sodium thiosulfate to the power m is equal to K2 divided by K1 multiplied by 1 over T, and then since K2 and K1 are both constants, we can write concentration of sodium thiosulfate to the power m is equal to K divided by T, or constant divided by T. Or in other words, now 1 over T, if you observed over here, 1 over T is going to be our rate, right? 1 over T, because you know K2 is a constant, 1 over T is going to be our rate, or we can say 1 over T is proportional to the rate. As you can see here, rate is equal to K2 divided by time. K2 is a constant. So then we can say rate is proportional to 1 over T. So over here we can very clearly observe that the concentration of sodium thiosulfate is proportional to rate. Concentration of sodium thiosulfate is proportional to rate, or in other words, concentration of sodium thiosulfate is equal to a constant divided by time. Right. And we know the concentration of sodium thiosulfate was equal to the volume of sodium thiosulfate. So in the tests that we carried out, in the 5 tests that we carried out, only thing that we changed was the volume of sodium thiosulfate that we used. So by changing the volume, we altered the concentration of sodium thiosulfate in the reaction mixture. So concentration of sodium thiosulfate is proportional to the volume of sodium thiosulfate used in each of these tests. So we can say concentration of sodium thiosulfate to the power m is proportional to volume of sodium thiosulfate used to the power m. So using 3 and 4, we can write, now this is the reaction 3 and this is 4. So we have now learned concentration of sodium thiosulfate is proportional to volume of the solution into the power m. So instead of sodium thiosulfate, we can plug in volume like we have done over here. So volume is proportional to constant K divided by T. When table readings are used, we can see in this particular table that we looked at earlier, bear with me a second. So we can see this particular table, the time it took when we were changing the volume of sodium thiosulfate at 25 cubic centimeters of sodium thiosulfate. The time it took for the observation to appear was 20 seconds. And when we used 20 milliliters of sodium thiosulfate, it took 25 seconds for the observation to come about. So while keeping that data in mind, we can observe when you use 25 cubic centimeters of sodium thiosulfate volume, you can observe the rate, or we can write this expression over here, 25 cubic centimeters to the power m equals to a constant divided by 20 seconds. And over here also, we do the same for another test, test 2. Test 2 used 20 cubic centimeters of sodium thiosulfate. So therefore, we can write an expression is equal to K divided by 25 seconds because it took 25 seconds for the observation to come about. If you take this expression 5 and 6 and divide, these constant values will get cancelled off, leaving behind only the numerical values. So at that point, now still the m value, which is the order of the reaction, is intact. Now if you take a look at this, you can very clearly see that these two data are the same. So that means when you divide 25 by 20, and you will get the same value here as well, which means m is equal to 1. M is equal to 1. When you divide these two, it gets to 1.25 into the power m equals 1.25, indicating m value is equal to 1. So with respect to sodium thiosulfate, the order of this reaction is 1. We have found out the order of the reaction with respect to sodium thiosulfate. Right. So we can see over here a graph that is going to be a small table that can be used to draw a graph given here. So you can see sodium thiosulfate concentration. Instead of just giving the volumes, we have the concentrations of sodium thiosulfate here. Now earlier on, we used the volumes to calculate the order. Now we have been directly given the concentrations of sodium thiosulfate for the same test. So instead of dealing with volumes, we have now converted the volumes that we used into concentration. And now we know the time it took. So we can, if you know the time it took for the specific observation to occur, we can calculate the 1 over T value for that particular test as well, for each of these tests. And then, since we know R is directly proportional to concentration of sodium thiosulfate into the power m, we also know that R is proportional to 1 over T. I mentioned that earlier, right? R was equal to K, or constant, divided by T, right? So when there is a constant divided by T, we can say directly R, or rate, is proportional to 1 over T. So using these two equations, we can say the concentration of sodium thiosulfate to the power m is proportional to 1 over T. So we know these things from the previous examples as well. We know sodium thiosulfate concentration to the power m equals K divided by T, or we can take the T over here and write this expression. That means if you take the concentration of sodium thiosulfate multiplied by the power m, and if you take the concentration of sodium thiosulfate to the power m multiplied by the time, it is going to be a constant for each test. Now students, let's take a look at a graph drawn between the concentration of sodium thiosulfate versus the time it takes for the observation to take place. Normally students, when you draw this graph, you can see it's a curved graph. Students, when you analyze a graph that is drawn between the concentration of a reactant versus time, you will observe three different types of graphs. So let's take a look at these three different types of graphs. The first type is, you will observe a graph where there is a straight line like this. So this is time, this is concentration, let's say reactant concentration, let's say X represent reaction, so the reaction concentration. If you have a graph where the reactant concentration decreases evenly over time, right? This straight lining indicates every passing minute the amount of change that has taken place is the same. So the gradient here is the same. Now students, this type of graph communicates to us that the order of the reaction with respect to reactant X is equal to 0. That means that the reactant X, let's say we are talking about a reaction where X plus Y turns into Z. So if the X concentration versus time graph appears this way, that would mean that the order of the reaction with respect to X is 0. Order of the reaction with respect to X is 0. That means concentration of the X reactant is not affecting the rate of the reaction. And then you have another type of graph where you will observe a curve like this. Again, we have time here. Let's say this is concentration. Again, we'll take X as the example. If the X concentration versus time graph appears this way, this could be either first or second order. First or second order. Now, if it is first order, because both first and second order graphs appear this way. Both first and second order graphs appear this way. However, usually second order graphs, or graphs drawn for concentration versus time, second order reactions usually would have a steeper curve. But you can't just look at it and assume, okay, this curve is steep, so this is second order, or this curve is not very steep, so therefore it's first order. You can't assume and actually come to a conclusion whether it is first order or second order. So it is important when you have a curved graph for concentration of reactants versus time, it is important to observe the half-life. Half-life means the time that it takes for the reactants concentrations to become half. So we have reactant concentrations here and the time it takes for the reactions concentrations to become half is considered to be our half-life, right? And then if you observe, now imagine this was this concentration was 2. For it to become 1, it took this amount of time. If you observe how long it takes for 1 to become half, again that means again to measure another half-life. If the half-life is always going to be constant in this type of graph, so imagine if the half-life ends up always being exactly the same or quite similar. At that point, students, you can say that this is 1 divided by 2, this is 1 divided by 4. You can see in each of these situations, the half-life value is the same. Now at that point, based on that observation, you can see that the order of the reaction with respect to the concentration, let's say order of the reaction with respect to the concentration of X, let's say it is M, so we can say this order is 1. Or in other words, order of the reaction with respect to the reactant X is 1. So you have to understand, before you make that decision, you need to observe first whether the concentration versus time graph is a curve. So there can be two graphs that presents a curve when it comes to concentration versus time graphs. So when order of the reaction is 1, you have a curve, and when order of the reaction is 2 also, you will have a curve. However, when the order of the reaction is equal to 1, if you observe the half-life of the reaction, you will see that the half-lives do not change as the reaction proceeds. However, if you draw a similar graph, for a second order reaction, the graph would appear quite steep, like so. So at that point, students, if you're trying to measure the half-life, right? Let's say this is 2, then 1 would be somewhere around here. So this is the first half-life. We'll call it T1. Right? And then this is going to be half that concentration again. You can see it is increasing ever so slightly. This is, let's say, T2. And over here, it is also increasing even more. T3. Right? Do you see that when you are talking about a second order reaction, or if the order of the reaction with respect to a specific concentration of a reactant is 2, at that point the graph drawn for that concentration versus time will have a very steep curve. But if you measure their half-lives, you will observe that the half-life value is not going to be the same. Earlier on, we observed the half-life values are exactly the same. But however, when it comes to this, you can see the half-life value is going to keep on increasing. So this, students, is how you identify whether the order of the reaction with respect to a specific concentration of a reactant is 0th order, 1st order, or 2nd order. If it is 0th order, you will observe a straight line like this when you draw a concentration of the reactant versus time graph. The gradient is going to be a constant. That means now gradient represents the rate, right? So that means the rate of the reaction has remained a constant while you saw a decline in the concentration of the reactant that we have here. As the reactant concentration goes down, the gradient remains the same. That means as the reaction concentration went down, the rate of the reaction didn't change. That means with respect to that particular reactant, order of the reaction was 0. So what happens if the order of the reaction with respect to a specific concentration or with respect to a specific reactant is 1? So let's say we have X here. With respect to X, if the order of the reaction is 1, the graph drawn for its concentration versus time is going to be a curve. And the most important part of this graph is the fact that the half-life is going to be the same. Now, half-life is the time it takes for the initial concentration of a reactant to be half. So you can see over here, let's say the concentration over here is 2m. For it to be 1m, it took t amount of time, or let's say t half amount of time. And then again, let's consider the initial concentration to be 1. And for 1 to be half, it took again the same amount of time. You can see that this amount of time is more or less the same. And then again, half to be a quarter, it took the same amount of time. So each time that we halve the concentration, for that concentration to be halved, the time it took was the same. So we say the amount of time that it takes for the initial concentration to be just half is referred to as its half-life. And if you measure few half-lives across this graph, you will see the half-life value of all of these situations is the same. So that means this is a first order reaction. In a first order reaction, if you draw a concentration versus time graph, the half-life values are going to be the same. If the order of the reactant or order of the reaction with respect to a specific reactant is 2, right, like in this case, then at that point you will see again another curve, but this curve will be a steeper curve. And the half-life values are not going to be the same. Half-life values are going to keep on changing. When the concentration goes down, half values are usually increasing. So these half values, when it comes to a curve like this, is not going to be the same. So if you have a curve where the half values are not going to be the same, we can conclude that it is a second order reaction. So let's go back to this graph that we have over here. So let's observe this graph here. So in this graph, the half-life values should be equal to one another. Let's observe that. So this is a concentration versus time graph for this specific reactant. And if the order of the reaction with respect to this reactant is 1, the half-life value should be the same. Right, let's see. Since 0.125 is a bit of a difficult place to start with, we can consider this to be our initial concentration for this particular observation, because it's a clear observation at that point. So the concentration over here that is given is 0.100. Half of that concentration is 0.050. So for that change to happen, for us to go from 0.100 to 0.050, we have spent 25 seconds. That is our half-life, right? So this is a half-life. Then again, we can measure a second half-life. We can see we have gone from 0.050 to 0.025, right? So let's find that half-life. So if you draw a small line here, it goes all the way up to this point. And what is that point? That is 75 seconds, right? So because this is 25, 50, 75, 100. So what is the gap between 50 and 75? Again, isn't it 25 seconds? So this is our second half-life, right? And even that second half-life had the same half-life value that we observed earlier. So you can see as this reaction goes on, each half-life is the same. The half-life values hasn't changed. So therefore, this we can conclude is a first order reaction with respect to sodium thiosulfate. So sodium thiosulfate's order was communicated as M, so that we can communicate that the order of the reaction with respect to sodium thiosulfate is 1, or in other words, M is equal to 1. Now students, we can draw a graph for 1 over T versus the concentration of sodium thiosulfate. So when you do that, you will get a straight line passing through the origin. Now students, over here 1 over T will serve as our rate of the reaction. If you remember, rate or R was equal to amount of change, let's say change in the concentration of sodium thiosulfate, or change in the amount of, we'll just write amount of change, because in this case we were measuring the amount of a specific, specific amount of sulfur that was produced, right? So amount of change divided by time. However, since we measured the same constant amount of change, right? The amount of change was the specific amount of sulfur that got produced, that was sufficient enough to cover the entire X mark, right? So the amount of change here remained a constant. So we wrote here R is equal to K divided by T. So whenever there is a constant like this, we can also say the rate is proportional to 1 over T. Rate is proportional to 1 over T. So we can say over here this is proportional to rate, and we have the concentration here. So you can see as we increase the concentration, the rate also has increased along with it proportionally. So whenever you draw a rate versus concentration graph like that, or 1 over T versus concentration graph like that, you can have three different types of these graphs. So I will draw those three different types of graphs here. Now the first type is, you might have a straight line without any change in the rate. The other one is a line passing through the origin, and the next one is a curve like so. So let's name these axes. This is our concentration. Let's say the reactant is X, right? The concentration here, and this is our 1 over T axis. This is our 1 over T axis. And this is again our 1 over T axis. Here, this is going to be our concentration. Let's say we take the reactant X like we did in the past examples. So students, if you draw a graph for concentration of X versus 1 over T, then if you get a graph like this, where it is a constant, where the rate is a constant, 1 over T represents rate here. So if 1 over T is a constant, as you increase the concentration of the reactants, at that point that would mean no matter how much you increase the concentration of reactant X, it has not affected the rate, because as I mentioned here, 1 over T in this case is proportional to rate. I will write that down here for easy reference. Rate is proportional to 1 over T. So that means if 1 over T has not changed when you keep on increasing the concentration of the reactant, that means the rate hasn't changed. So when you have a graph like this, that would mean the order of the reaction with respect to X, the order of the reaction is 0. With respect to X, the order of the reaction is 0. When you have a graph where when you keep on changing the concentration, if the 1 over t values also keep on increasing, that means 1 over t means again the rate. If the rate keeps on increasing proportional to the increase of concentration, like this, it is going to mean that the order of the reaction with respect to x is 1. And if you see a graph like this, as you keep on increasing the concentration, if the rate keeps on doubling, right? So for example, if let's say this is x1 concentration and this is basically 2x1, right? That means we have doubled the concentration of this particular location. So at this point, the rate, we'll call the rate R1. And at this point, the rate would be 4R1. Right, students? So in a graph like this, what you're going to observe is when you double the concentration, the rate will not be just doubled, rate would not just be doubled, it will be quadrupled. Right? So when the order of the reaction is x to the power 2, or when the order of the reaction is 2 with respect to x, this is what happens. When you double the concentration of the reactant x, the rate of the reaction will not be just doubled, instead it will be quadrupled. So this is the graph that you will observe for a second order reaction with respect to x. So students, if the order of the reaction with respect to x is 2, you would observe a graph like this. It's a curve. So if you draw the rate versus concentration graph for x, it is going to be a curve, and one thing that you observe is when you double the concentration of x, the rate would be quadrupled. And when it comes to a first order reaction with respect to x, you are going to observe when you draw a concentration versus time graph, you are going to observe a line, straight line going through the origin. So in this case, you will see that when you increase or when you double the concentration of x, the rate will also be doubled. When you double the concentration of x, the rate will be doubled, or in other words, the concentration is going to be directly proportional to the rate. As you increase the concentration, or when you double the concentration, the rate will be doubled. And in this case, we see when the order of the reaction with respect to x is 0, when you increase the concentration of x, the rate will not change, rate will stay the same. Right? At that point, we can determine the fact that the concentration of x has had no influence on the rate of the reaction. So therefore, there is a 0 order reaction with respect to x. So in this case that we have over here, we have a straight line passing through the origin, and you can see due to that reason, this is a first order reaction. So we can write order of the reaction, which was signified by m earlier onwards, is equal to 1 with respect to sodium thiosulfate concentration. Order of the reaction with respect to sodium thiosulfate is 1. Then we move on to the next part, the impact of reactant concentration on rate of reaction between sodium thiosulfate and nitric acid. But in this section, we are going to focus on changing the concentration of nitric acid while keeping the concentration of the sodium thiosulfate a constant. Now, in the earlier setup, we changed the volume of sodium thiosulfate that we added to the reaction mixture. In this particular set of experiments, concentration of nitric acid has not had an effect on the rate of the reaction. We can see as we keep on changing the concentration of nitric acid, the time taken for the same observation to appear has not changed. What does that tell you? That tells you that although you change the concentration of nitric acid, the rate of the reaction has not changed. The rate of the reaction has not changed. So therefore, students, we can say that the order of the reaction with respect to nitric acid is 0. We can say it there itself by observing these results. However, we can move on to drawing graphs and calculations as well. So we follow the same set of steps when carrying out this second set of experiments. So determining the rate or determining the reaction order with respect to nitric acid, and in this case we have sodium thiosulfate and nitric acid and water in one beaker, and as soon as you mix the two reactants together, we will start the stopwatch and we will observe how long it takes for the X mark to disappear. Determining the reaction order with respect to HNO3, or in other words finding N. N was referred to as the order of the reaction with respect to nitric acid. Involves positioning a clean glass beaker on an X-marked white paper, followed by addition of sodium thiosulfate and water, subsequently adding specific volume of nitric acid all at once, while maintaining a constant eye level above the beaker. The time taken for precipitate to cover the X mark is measured using a stopwatch. Given the constant concentration of sodium thiosulfate solution, if rate of the reaction is denoted as R, we can write rate is equal to K1, which is the rate constant, multiplied by HNO3 to the power 1. So here K1 not only includes rate constant, we consider the concentration of sodium thiosulfate is also constant, right? So considering all of that, we can say R is equal to K1 multiplied by the concentration of nitric acid to the power N. So in this case, again, like we mentioned in the earlier cases, the amount of change divided by time is going to be equal to the initial rate, and amount of change is a constant here. So therefore, we can say the same thing that we said earlier, R is equal to a constant divided by time. So the quantity of sulfur produced remains consistent across all of the experiments. So therefore, we can move on to this expression. We know that R is equal to a constant divided by T. So we can say that constant is K2. K2 divided by T is equal to K1 into concentration of nitric acid to the power N. Now we have derived this rate equation earlier, and now we have just derived this rate equation. We can make those two equal to one another, and at that point we can come to this conclusion where K2 divided by K1 is equal to nitric acid concentration to the power N multiplied by T. Since K2 divided by K1 can be given as a constant value, we can write nitric acid concentration to the power N multiplied by time is equal to a constant. So if you have concentration of nitric acid multiplied by time, it should always be a constant. So we came to the same equations earlier on as well, students. So since we changed the concentration of nitric acid by varying the volume of nitric acid we took into the reaction mixture, we can say the concentration of nitric acid is proportional to the volume of nitric acid we took. So therefore, we can say the same, we can write the same expression with the use of a volume of nitric acid as well. And based on the observations here, we can see when we use 5 cubic centimeters and 4 cubic centimeters in test 1 and test 2, the time it took for the same observation to appear was 20 seconds. So based on that, we can write these two expressions, and if you divide these expressions, you will get to the final answer over here, that N, the order of the reaction with respect to nitric acid, is 0. The order of the reaction with respect to nitric acid. And plus, students, here it should be we are dividing we are dividing not 1 by 2, we are actually dividing 3 by 4, right? So we are dividing 3 by 4 and you are getting to the same answer, which is n is equal to 0, because you can see when you divide 5 cubic centimeters by 4, since in both of these cases there's a power of n, we can take the power of n outside, and when you divide these two together it's going to be equal to 1. So 5 divided by 4 is 1.45, and still the power of n is still there. And when you have a power of 0 over any number to the power 0 is going to be 1. So over here 1.25 to the power 0 is equal to 1. So therefore n should be 1. So that means order of the reaction with respect to nitric acid is going to be 0. Thus, in the reaction between nitric acid and sodium thiosulfate, the term n is equal to 0 concerning nitric acid. That means when you keep on changing the nitric acid concentration, the rate of the reaction does not change, as the nitric acid's order of the reaction is 0. So students, this table shows us the same experimental data that we saw in the previous graph, but the difference is we have now included the concentrations of nitric acid instead of just the volume of nitric acid, and apart from that we have also included the 1 over T values as well. So using the concentration and the time, we can draw a graph. So you can see as we keep on changing the concentration, the time it takes for a specific observation to appear has not changed, right? The time it took for a specific observation, which is the collection of a specific amount of sulfur, to appear has not changed. Now, even if you draw a graph over here where the concentration of, if you draw a graph between concentration and rate of the reaction, that is also going to appear the same way, right? So if you draw another graph over here, concentration of HNO3 concentration versus rate. So rate can be written as 1 over T. In this case, as we have seen, 1 over T is proportional to rate. So at that point you will see a straight line, or the constant value will be observed when you keep on changing the concentration of nitric acid. If the nitric acid concentration is increased or decreased, still the rate of the reaction is going to be the same. Now, similar observations can be observed here as well. As you keep on increasing the concentration of nitric acid, the time it took for a specific observation to appear has remained a constant. When you keep on increasing the concentration of nitric acid, the 1 over T value, or in other words, rate of the reaction, has remained a constant. Now, over here, we have the rate expression written. Rate expression is equal to rate constant multiplied by concentration of sodium thiosulfate to its power m, and nitric acid concentration raised to its power n. We know the order of the reaction with respect to nitric acid is 0, so therefore we don't have to include the concentration of nitric acid. Although the presence of nitric acid is important to carry out the reaction, the order of the nitric acid, or order of the reaction with respect to nitric acid, is 0. So therefore the concentration of nitric acid does not play a role in determining the rate of the reaction. So the rate equation is going to be written like this: R is equal to rate constant multiplied by the concentration of sodium thiosulfate. So there is a power 1 here because the order of the reaction with respect to sodium thiosulfate is 1, but we don't have to indicate just 1. If it is anything greater than 1, at that point you will write the number, but if it is just 1, you will not be writing the number. So the combined order of this reaction is going to be 1. So the overall order of this reaction is 1, because there are although there are two reactants, with respect to one reactant, the order of the reaction was 0. With respect to the other reaction, the order of the reaction was 1. So when you add 1 and 0 together, you get the overall order of the reaction. So 1 plus 0 is 1 itself. So the overall order of the reaction happens to be 1. Observations from the reactions involving sodium thiosulfate and nitric acid. So when you mix these two, what do you observe? The initial observation is the formation of a milky reaction mixture. The milky appearance is due to the formation of solid sulfur. So students, in this slide, we are talking about the fact that we can produce sulfur by reacting any of these acids, nitric, HCl or sulfuric acid with sodium thiosulfate. In fact, we can use this experiment to identify sodium thiosulfate ion. So if you react sodium thiosulfate with HCl, nitric or sulfuric, one of the key observations would be the formation of a milky solution while producing a pungent, suffocating odor. So over here we have that observation written. So when you react HCl with sodium thiosulfate, you will see formation of a yellow color precipitate along with a pungent and a suffocating odor. So students, when you add HCl to sodium thiosulfate or any thiosulfate ion solution, you are going to first observe that the reaction mixture is turning milky in color, and this is not just going to be white, it's going to have a yellowish color to it. So that indicates the formation of solid sulfur. And apart from that, you will also observe or you will also feel that there's another gas being produced, and this gas is going to be very pungent in odor, right? It will have a pungent and suffocating odor, so it will be very evident gas has been produced, and the gas that is produced here is sulfur dioxide. The gas that is produced here is sulfur dioxide. And when it comes to reacting HCl and sulfite, right, in sulfite ion, you do not see the formation of sulfur. Instead, you only see the formation of, or you only observe or note the formation of a pungent suffocating gas. So we know what is a pungent suffocating gas, that is sulfur dioxide. So only sulfur dioxide is produced here. But if you add an acid to sulfate ions, you will not observe a change. So if you add H plus to S2O3 2 minus, if you add H plus, you'll be forming sulfur solid and sulfur dioxide. Some of it will be dissolving in water, but we'll write it as a gas here. And apart from that, water will also be produced, right? So over here we need two H pluses. Now you can see these are the things that get produced when you react sodium thiosulfate with water. Sulfur produced is going to turn the reaction mixture milky, and the precipitate has a yellowish color to it, and the pungent suffocating gas is going to be sulfur dioxide. And when it comes to sulfite, SO3 2 minus, sulfite reacted with H plus or acid brings in H plus ions, will produce sulfur dioxide along with water. So the pungent gas is sulfur dioxide, right? So if you balance this off, you have two H pluses reacting with sulfite ions to produce sulfur dioxide gas and water. If you add sulfate ions and H plus ions together, you will not see a change. So you can see no change or no observation. Right, students, so that is something you have to keep in mind. We can use this particular reaction where you react thiosulfates with acids as an identification test for thiosulfate. So at that point, thiosulfate ions, when reacted with acids, will produce sulfur solid as well as sulfur dioxide. Explanations to how nitric acid concentration affects the rate of the reaction between sodium thiosulfate and nitric acid. In the reaction between sodium thiosulfate and nitric acid, in the reaction order with respect to nitric is determined to be 0. This suggests that the reaction mechanism likely involves 2 or more steps, with steps involving the participation of reactant nitric acid occurring at a relatively higher rate. So let's explain that statement in the coming slides. So first of all, over here in this slide, it says very clearly, although there are two reactants reacting together, students, when you have observed, when just two reactants are there, if it is an elementary reaction, both of the reactants concentrations are going to determine the rate of the reaction. However, in this particular reaction, you see nitric acid's concentration did not matter. When we change the nitric acid concentration, we observe the rate of the reaction didn't change. That means nitric acid concentration was not able to change the rate of the reaction, right? So the order of the reaction with respect to nitric acid was 0. This indicates that this reaction that we wrote between nitric acid and sodium thiosulfate is not a single step reaction. If it was a single step reaction, nitric acid concentration should have mattered, but this must be a multi-step reaction. And in a multi-step reaction, in a reaction where there are few different steps, the rate of the reaction is determined by the slowest step. So when we say that nitric acid involving reaction must be happening in a relatively faster rate, that is true, right? So we will explain that in detail later. So over here we have the same reaction given, just to give you the idea of what is taking place here. When you react these two together, this is going to be our balanced chemical equation that we observe, and this is the rate expression, and we know that the order of the reaction with respect to nitric acid is 0. So therefore, when you are writing the rate expression, even if you write without including this with the real numbers, real values, when you write with the real values where m is actually equal to 1, at that point you don't have to include nitric acid. Why? Because now this is our initial starting point, but after actually finding out the order of the reaction of nitric acid, we can write the rate equation just like that and leave it at that. We don't need to include the nitric acid concentration there. Why? Because the order of the reaction with respect to nitric acid is 0. Anything to the power 0 is 1. Any numerical value to the power 0 is 1. So therefore, we don't have to worry about that here. And this is the reason why we do not observe nitric acid's concentration having an impact on the rate of the reaction. So the reaction must be happening in 2 or more steps. Now let's assume the reaction is happening in 2 steps. So when we are talking about a reaction that is happening in 2 steps, for each step there will be an activation energy. Let's say for the first step the activation energy is EA1, and for the second step we can say the activation energy is EA2. This small gap over here is our activation energy 2. So we can see the activation energy 2, or for the second step the activation energy value is quite small, and for the first step the activation energy value is quite large. So when you have a large activation energy for a given step, that particular step happens very slowly, and when it comes to a step that has very small activation energy, that step will happen relatively fast. So this second step has a very small activation energy compared to the first step. So the second step is happening relatively faster. And as I mentioned earlier, in a reaction mechanism with multitude of steps, in a reaction mechanism where there are many steps, the step with the slowest speed, is going to determine the rate. So the step with the slowest speed will also have a higher activation energy. So this particular step is going to be the step with the slower speed compared to the two steps here, and this step will determine the rate of the reaction. So we saw, when you're talking about the rate of the reaction, only one concentration or one reactant mattered, and that reactant happens to be sodium thiosulfate. So that means this particular step that we have over here, the first step must be the step that is affected by the concentration of sodium thiosulfate, because this step very clearly is the one that is determining the rate of the reaction. So therefore, this step must be the one that is affected by sodium thiosulfate. And this second step has a very small activation energy, so therefore it is happening faster, and that must be the step affected by the concentration of nitric acid. Right? So students, as you know, in chemical kinetics we learn this. When it comes to an elementary reaction, it's a different story. That means in an elementary reaction, if you have two reactants, both of their concentrations will influence the rate of the reaction. But in a multiple step reaction, the slowest step will determine the rate of the reaction. We say the slowest step is the rate determining step. And majority of the time when you observe the reaction progression graphs like this, you will see that the step with a higher activation energy usually have very slow speed or small rate. So when you have really high activation energy, that step will be happening in a very slower rate, and therefore that will determine the rate. And the rest of the steps are usually happening in a faster rate. So that is not going to be the ones that are determining the rate. So if you can't comprehend this, one of the things that you can think of is in an assembly line. If you have an assembly line where, let's say, you are trying to send some letters to some recipients, and in your school you have assembly line of, let's say, 3 people, and the first person has to, let's say, paste the stamp on the cover letter, or paste a stamp on the envelope, and the second person has to write the address, right? And the third person has to, let's say, make sure they write the return address. So if the second person takes a very long time to write the correct address, then what happens? Although the first and the third person does their job really fast, if the second person is very slow, at that point the entire assembly line speed is going to be determined by the second person. Right? So the speed of that process will depend on the second person. So just like that, when it comes to a reaction that is happening in multiple steps, the overall speed of the reaction or the rate of the reaction will depend on the slowest reaction or slowest step. So we say the slowest step is usually the rate determining step. Step 1 has the highest activation energy, and therefore it becomes the slowest step. The slowest step in a reaction also determines the rate of the reaction. This step is a step that is affected by the concentration of sodium thiosulfate. Moreover, the second step has a lower activation energy and happens to have a relatively faster speed compared to the first. This step involves nitric acid. The second step does not determine the rate of the reaction. So the same things that I mentioned earlier is mentioned here as well. Therefore, the increasing acid concentration does not alter the reaction rate or the time that it takes for the reaction to produce a constant amount of sulfur. The acid concentration does not influence the rate of the reaction. The acid concentration does not influence the rate of the reaction. So therefore, the rate expression would only include the reactant that was found in the slowest step of the multiple step reaction. So this particular reaction happens in multiple steps, and the slowest step determines the overall rate of the reaction, and in the slowest step, whatever the reactants that are present is going to determine the rate of the reaction. So in the slowest step, the only reactant we found was sodium thiosulfate. So therefore, the rate expression will only include reactants that are found in the slowest step of the multiple step reaction. Important: if the balanced equation of a chemical reaction is given without presenting any mechanism, it is impossible to discern how reactant concentrations impact rate solely from the overall reaction. You can't just by looking at it assume that it is a single step reaction or a multiple step reaction. Or in other words, you can't just by looking at a reaction assume that it is an elementary reaction. If it is an elementary reaction, at that point, all of the reactants that are present in the reaction will influence the rate of the reaction. However, just by looking at a reaction's balanced equation, you can't decide whether it is an elementary reaction or a multiple step reaction. So the order of the reaction is determined through experimental analysis, just like we did in this experiment. Measures were implemented to ensure an identical degree of change in each test, and we are going to take a look at those measures. So when we were carrying this test out, we needed to make sure the amount of sulfur produced in this experiment remained a constant. So we are going to take a look at what measures were used to make sure the amount of sulfur that is produced remained a constant. So we have nitric acid mixed with sodium thiosulfate, and we observe the beaker containing the reaction mixture from a fixed position. So that is given here. Upon combining the reactants, the stopwatch was initiated. Subsequently, the X mark at the base of the beaker was monitored from a fixed position. You can't first monitor it from here and then monitor it from somewhere above, right? You can't first monitor it from here and then later on in the second experiment you can't start monitoring it from here, right? So you shouldn't be doing that. You have to keep monitoring it from the same point. So you keep monitoring it from a fixed position until it becomes obscured by the formed precipitate. Upon reaching the point where X mark is no longer visible, the stopwatch was stopped and the time taken for this observation to take place was recorded. So students, the precipitate that is formed will cover the X mark, and at one point we will no longer be able to see it. You have to press, we have to stop the stopwatch as soon as we stop seeing it, right? Because as you allow time to pass by, you will see more and more sulfur will come, and even after about a couple of minutes past it initially covering the X mark, it is still not visible. So we have to stop the stopwatch as soon as it first covers the X mark completely, rendering it invisible to us, or covering it completely, not allowing us to see the X mark. Guidelines for each test: maintain uniform cross-sectional area of the beaker, or you can use the same beaker as well. As I mentioned earlier, if you use a beaker with a different cross-sectional area, at that point the amount of sulfur that is needed to cover the X mark in a way that it is not visible to us will be more. So as the cross-sectional area is larger, then there will be more and more sulfur needed to bring on the same effect, right? So you need to make sure the cross-sectional area of each beaker that you use is the same. If not, you can resort to using the same beaker. Use consistent white paper with identical marks. So if you have the ability to use the same white paper with the same white mark, use it. Otherwise, you can have few white papers with the same mark, right? So you need to make sure the X mark that you use is identical or the same X mark. So in our experiment, we use the same X mark that is printed on a piece of paper. We do not change the X mark throughout the experiment. Ensure one individual takes all readings. Make sure that only one individual takes all the readings. Again, there can be human error, and if it is just one individual that is taking it, that is not going to be a problem because it will be consistent. However, if few different individuals take readings for different tests, at that point you will not be able to obtain more precise data because of the fact that different individuals have different types of errors. Conduct test at room temperature. Don't allow the temperature to change, because if you change the temperature, as you increase the temperature, as you know, when you increase the temperature of a reaction mixture, the particles or overall energy of a system will increase, which will lead to increased reaction rate. In adherence to specified guidelines, during the tests, the consistent formation of sulfur renders the mark invisible. In these tests, the amount of change can be regarded as a constant, right? So we have seen this reaction so many times, we know at that point R is equal to a constant amount of change divided by time. Describing the difference observed between conducting the test at 25 degrees Celsius, which is laboratory conditions, and heated conditions, which is 40 degrees Celsius. Now students, if you keep everything else in the experiment a constant, that means if you keep two sets of experiments where the concentrations of both the sodium thiosulfate, nitric acid in both the reaction mixtures are the same. However, if you conduct one reaction at a higher temperature like 40 degrees Celsius, and if you conduct one at room temperature, you will observe the one that is heated will have a higher rate. The same observation that we are trying to get here will occur at a smaller time frame, right? So we can conclude that the reaction rate was higher at higher temperatures. So why is this? So that is what we try to discuss over here. When you carry out the same experiment in all the identical conditions except for the temperature, at that point we will observe that the time taken for the same observation to occur will be smaller in higher temperatures. That means the rate of the reaction in higher temperatures were greater. In the reaction between sulfuric and nitric, or any reaction, when you are carrying out a reaction, according to our chemical kinetics, we know there should be collision between particles. There should be collision between particles for the reaction to take place, right? So apart from these collisions, students, it is also imperative, it is also very important to have collisions in the right orientation. Then apart from the orientation also, it is important for the particles to have the right amount of energy, which is also categorized as the activation energy. The minimum amount of energy needed for the reactants to turn into products is going to be referred to as the activation energy. So students, when we are increasing the temperature of a reaction mixture, now we have learned, first of all, there's something called the activation energy. Basically, the activation energy is the minimum amount of energy the particles need in order to have a successful collision. Now, a successful collision is a collision that takes place with the right amount of energy as well as the right orientation. So, for a successful collision to happen, we need to have mainly two things: a collision that is happening with the right orientation as well as particles having the right amount of energy. So, the minimum amount of energy that will allow a successful collision is usually referred to as the activation energy. Any particle that actually has a higher energy than the activation energy can move on to a successful collision if they collide in the right orientation. Right? Even with the correct amount of energy, they still can collide with wrong orientations. But if they collide with the right orientation and the right amount of energy, it results in forming products. So, if you take a look at this graph over here, let's say this is the fraction of molecules. This is the fraction of molecules or particles that have a specific amount of energy, and this is our energy axis showing the energy of particles, right? So in a normal sample of reactants, they will have this type of energy distribution, a bell-shaped curve, right? Majority of them will have average amount of energy. And students, apart from that, you will observe that some will have, or when it comes to a specific reaction, there's going to be activation energy value. Let's say, now I will write over here activation energy and I'll leave it at that. I want you to understand, when I draw this curve, we can observe that there is a small fraction of particles that will have a small amount of energy, very small amount of energy, and there is a very small fraction of particles that has an extremely high amount of energy, and majority of the particles have an average amount of energy. And only the particles that have energy greater than the activation energy, right, which means this fraction, only this amount of particles are capable of having successful collisions. Because for successful collisions to take place, one of the requirements is having the relevant amount of energy, which is energy greater than the activation energy. So if particles have energy greater than the activation energy, they can have successful collisions. So there's another requirement. Just because you have right amount of energy doesn't mean they're going to have successful collisions and produce products. Apart from that, you need to have the right orientation as well. So let's say this is the energy distribution at room temperature 25 degrees Celsius, and I will draw the next graph in, let's say, red color. Now, if you increase the temperature, now this area under this particular graph represents the overall number of molecules. So when you are drawing another graph, keep in mind the area under the graph shouldn't change. So when you normally increase the temperature, students, what happens is the overall average energy value of the system increase, because when you increase the temperature, energy will be given to the system. So average energy value of all the particles in the system will increase, right? Each particle will have a higher kinetic energy. So due to that, this curve actually gets shifted to the right. So when you are shifting a curve to the right, to the higher energy side, we usually draw the peak of the graph somewhat lower than the previous graph and towards the right, right? Towards the right. When you shift the graph peak towards the right, you have to always make sure the peak is below the original peak. You can see the initial peak was here, and the next one is drawn below that peak when you are shifting the average value to the right. So when you do that, you can see if the activation energy doesn't change, the energy requirement, activation energy is the minimum energy requirement for successful collisions. You will see the overall number of particles that exceed this activation energy value or energy barrier is now much greater. So the number of particles, or the fraction of particles that are able to engage in successful collisions are now much greater. Now, due to these, students, we will observe a higher reaction rate at a higher temperature. Earlier, at a lower temperature, there was only a small fraction of particles that were capable of ending up in successful collisions, and now, due to the elevated temperatures, we can see the energy of the system has changed, and there are now much more particles that are capable of having energy that is greater than the activation energy, so they are capable of engaging in successful collisions. So therefore, the frequency of successful collisions will go up, increasing the rate of the reaction. Apart from that, even the collision frequencies will increase at high temperatures. When you increase the temperature of a system, particles will absorb energy and will start to move faster, right? That means the collision frequencies will also increase. All of these together will increase the rate of the reaction at a higher temperature. So the red color graph that I have drawn over here represents the 40-degree situation or increased temperature, and the black color graph that I have drawn over here represents our 25 degrees Celsius temperature condition. All right. So that is how we can explain this situation. So in this slide, we learned about what elementary reactions are. Chemical reactions occurring in a single step are termed elementary reactions. We observed earlier as well, there are certain reactions that are happening in multitude of steps. So those are not elementary reactions. Elementary reactions are reactions where there is a single step, or the reaction is happening in a single step, right? So those are known as elementary reactions. So after that, we learn about molecularity. The count of participating reactant molecules within a balanced chemical reaction is termed molecularity. Molecularity. Right. So if you take a look at this table over here, you can see balanced chemical equation of the reaction. Now let's consider all of them to be elementary reactions. And over here, we have the molecularity of each of these reactions. Now, molecularity is basically the total number of molecules that take part in forming the reaction, So you can see the first reaction, there is 1A and 2B reaction to produce 1C. So the type of two different reactants are A and B. But molecularity is not talking about the two types of reactants. They are talking about the overall number of molecules that are reacting to form products. Over here, with 1A, 2B are used. Altogether, how many reactants are used here? 3 reactant molecules. Now, 2 of them are B and 1 of them are A, right? There are only 2 reactant types. However, the overall number of reactant molecules is 3. So therefore, it is the molecularity of this particular reaction is 3. We say trimolecular, and then when you have only 2 reactant molecules, we say it is bimolecular. When there's only 1 reactant molecule, we say it is unimolecular. The relationship between order of reaction and molecularity. Molecularity of elementary reactions is similar to the order of the reaction. So for example, we have an elementary reaction here, right? We saw this elementary reaction earlier as well, given in the previous slide. So we can see this particular elementary reaction is involving 3 reactant molecules, 1A and 2 B molecules. So basically, overall 3 reaction molecules are there, and we can actually identify that this is a single step reaction. As we can see, there's only one activation energy value that we can see for this particular reaction in the energy diagram. We can see there's only one activation energy value. It is not happening in a couple of different steps. If it happens in 2 different steps, we will see 2 peaks with two very distinct activation energy values. So, and another thing is, students, just by looking at a reaction, we can't assume whether it is a elementary reaction or a multi-step reaction, right? So, the question that you are doing, or whatever the information that you have revolving around a reaction, should state that it is an elementary reaction for you to understand that it is an elementary reaction, or else they should give you the energy diagram like so. Right. So, in this case, the reaction is a single step reaction. When applying the rate law, if the rate of reaction is R, at that point, students, in elementary reactions, one of the most important parts is when you're writing the rate law. When you're writing the rate law, or when you're writing the rate expression, the rate expression can be written very easily this way. You just have to write rate is equal to rate constant multiplied by each of the reactants raised to their stoichiometric ratio, stoichiometric coefficient. So, the stoichiometric coefficient of A is 1. So, A's concentration is raised to the power 1. And B's stoichiometric coefficient was 2. So, the stoichiometric coefficient of B, which is 2, is raised to B's concentration, right? So, for an elementary reaction, if it is an elementary reaction, for example, if you write it as this, let's say X plus Y is turning into, let's say, Z, right? Let's say their stoichiometric ratios happens to be 4 and let's say 7 here, or we'll take smaller values here just so that it will be easier for us. We'll take 3 and 2. And if this is given, if the information is given that this is an elementary reaction, the rate can be written as rate is equal to K multiplied by concentration of X raised to its stoichiometric coefficient. So, the stoichiometric coefficient is the number that is written in front of X in the balanced equation. So, stoichiometric coefficient of this is 3. So, we have raised it to the power of X concentration. And then this has to be multiplied by concentration of Y raised to its stoichiometric coefficient, which happens to be 2. So, this is the rate equation for an elementary reaction. Right. The order of the reaction with respect to A in this reaction is 1. The order of the reaction with respect to B in this reaction is 2, because we saw the reaction was 1A reacting with 2B, right? So, the total order of this reaction is 3. Now, total order is where you add the overall order, actually where you calculate the overall order of the reaction. So, with respect to each reactant, there will be different orders. If you add them all together, you get the overall order of the reaction. So, we have order 1 with respect to A and order 2 with respect to B. So, if you add them together, it will be 3. The molarity of the reaction is also 3. So, we can see overall order of the reaction as well as the molarity of the elementary reaction happens to be the same. So, when you're talking about elementary reactions, the molecularity, not molarity, molecularity of the molecularity of the elementary reaction as well as the order of the elementary reaction is going to be the same. Therefore, molecularity of an elementary reaction equates the total order of reaction. In this case also, you will observe this is a single step reaction. They say that this is a single step reaction, that means this is a elementary reaction. In an elementary reaction, we have two reactant molecules reacting together to form one product. Now, we can see again there's only one activation energy value here. So this is a single step reaction. And when you are considering this, since we have only one reactant and the stoichiometric coefficient of that is 2, we can write the rate equation as R is equal to K, A concentration to the power 2, right? So K signifies the rate constant. And the overall order of this reaction is 2. So therefore, the overall order of this reaction is 2, as well as the molecularity of this elementary reaction is 2. We can see overall order and molecularity is the same when it comes to elementary reactions. One more example. As you can see, this is also a single step reaction. They have given the information here, and so therefore we can call it an elementary reaction. And we can observe that the order of the reaction for something like this, since you know that this is an elementary reaction, we can directly write it as R is equal to rate constant multiplied by the reactant, only reactant that you see over here, raised to its stoichiometric coefficient, which is 1. Usually we don't indicate the 1, but if it is any other value than 1, you would write it. So this is going to be the rate expression. And we can see the overall order of the reaction is going to be 1, and even the molecularity of this reaction is also 1. So both overall order, the reaction order, and the overall order is going to be 1, and the molecularity is also 1. So this serves as a final example to the fact that when you are considering elementary reactions, the overall order of the elementary reaction equates or will be equal to the molecularity of the reaction. So students, after learning about elementary reactions and how molecularity and the overall order of the reaction is equal to one another, we can move on to analyzing this reaction. We can see 1 sodium thiosulfate reacts with 2 nitric acid, right? So if the rate of the reaction is denoted as R, we experimentally found out the rate of the reaction is this. Rate of the reaction was just this. We found this out experimentally. So the overall order of this particular reaction that we experimentally found out was 1. However, if this reaction was an elementary reaction, right? We were not given the information initially whether this was an elementary reaction or not. However, if this was an elementary reaction, the overall order of the reaction must be equal to the molecularity of this reaction. Molecularity of the reaction is 3. So therefore, the overall order should be 3. So we can very clearly see that the overall order of this reaction is not 3, which would mean that this particular reaction is not an elementary reaction. So the molecularity of the reaction does not align with the total order of the reaction. Thus, this reaction is not an elementary reaction. So therefore, we can conclude the fact that this is not a single step reaction. It is a multi-step reaction. And we can see over here, we have drawn a graph indicating how the activation energy values keep changing. So we can, for example, if I give you a small example, since we haven't learned about the mechanism of this reaction, we'll just take an arbitrary example. Let's say we have 2 steps in a reaction, right? Let's say the overall reaction is you react A and B together, let's say to form D, right? This is the overall reaction that is given to you. But this is not an elementary reaction. That means this is a multi-step reaction. Multi-step reaction. Let's say step 1. In step 1, we can say 2A reacts with one another to form, let's say, C. And this has a really high activation energy. We can say this particular reaction has high activation energy. Activation energy value is really high. and this reaction therefore is going to be quite slow. And then the second step takes place after that. Let's say second step takes place. Actually, we'll write the equation as follows. We'll modify the equation a little bit. We write 2a plus 1b. Right. So then the second step would be, let's say, C reacting with B turning into D. So at that point, we can say that the second step actually, let's say, have a very small activation energy. Activation energy is small. So therefore, what can we say about the overall rate of the second step? It will be fast. Therefore, it will be fast. Now, I told you, when it comes to a multi-step reaction, the overall reaction is the addition between the two steps in this case. In this case, if you try to add these two together, you can see if you cancel the similar reactants or products that are present across the arrow, C and C will cancel off. So the overall reaction would be 2A plus 1B turning into D. This is the overall reaction that you observe, right? The same as what we have written here. But it actually happens in two steps. And one of the steps has a really high activation energy, so therefore it is happening very slowly. The other one is having slow activation energy or small activation energy, so therefore it is happening fast. So the rate of the reaction is going to be determined by the reaction that is happening slow. So this is going to be also known as the rate determining step. This is also known as the rate determining step. So the rate determining step is a slow step, and this particular reaction will be the one that will be determining the rate, and the only reactant that will appear in the rate expression is going to be A. B will not be appearing in the rate expression. So you need to understand that. So over here as well, when you're analyzing here, we can see this happening in two steps, and the step with the higher activation energy. Over here we have a higher activation energy, right? This activation energy is greater, and this activation energy is smaller, right? This is, let's say, activation energy 2. So one with the high activation energy, this particular step will be happening slowly, and this is the step that includes sodium thiosulfate, and that is why only sodium thiosulfate appears in the rate determining step, because this particular step happens very slowly and the second step happens relatively faster. So therefore that will not have an impact on the overall rate of the reaction, because the second step will happen really fast, the first step will happen very slowly. So therefore the slow step will determine the rate of the reaction. With that, students, we conclude the theory parts revolving around experiment number 31. Now we can move out of the classroom and into the lab to actually complete this experiment. So I'll see you in the lab. GCE Advanced Level Chemistry Practical Series, experiment number 31. Experimentational determination of the rate of the reaction between sodium thiosulfate and nitric acid, and effects of the concentration of the reactants towards the rate of the reaction. So the aim of this practical is to observe how the rate of a given reaction will change with respect to the concentration of the reactants, as well as we are going to look into how to calculate the order of a reaction with respect to each of the reactants. Now let's move on to the reagents and the equipment we'll be using to carry out this practical. Let's take a look at the reagents and the equipment we will be using for this practical. we'll be using nitric acid. The concentration of the nitric acid that we have here is 3.0 moles per decimeters cube. And then we have filled this 3 moles per decimeters cube concentrated nitric acid into this burette here. So it will be easier for us to measure the small volumes required for this practical. And then we have sodium thiosulfate. So sodium thiosulfate is taken in the concentration of 0.15 moles per decimeters cube. And again, we have filled the second burette with that particular sodium thiosulfate solution. We'll be using 3 different beakers, each labeled with the relevant reagent that we'll be taking into those beakers: sodium thiosulfate, nitric acid, and distilled water. And we'll be using a piece of paper with an X marked on it. We'll be using a measuring cylinder and a stopwatch. Now, let's move on to the practical, where we will be mixing these reagents together and observing a reaction happening. Now, let's take a look at how we conduct this practical. As you know, students, when it comes to measuring the rate of a reaction, there are a few ways that you can measure the rate of a reaction. First way would be to measure how fast the reactants are getting used up. Second way would be to measure how fast a product is being produced. So, we in this particular reaction will be focusing on how fast a product is being produced. So, when you mix sodium thiosulfate with nitric acid, solid sulfur will be produced. So, sulfur will be produced as a precipitate. Apart from that, sodium nitrate, sulfur dioxide, and water will be produced. So, when it comes to this particular practical, what we are going to focus on is the amount of sulfur that is going to be produced. So, we are going to make sure that we produce a constant amount of sulfur, and how we are going to make sure that we produce a constant amount of sulfur is by using this setup. We will mix the 2 reagents and we will add a little bit of water to make sure we have a constant volume of reaction mixture, and we will measure how long it takes for a constant amount of sulfur to be produced. So, I keep referring to this constant amount of sulfur. How do you measure a constant amount of sulfur that is produced? As sulfur is produced as a solid or as a precipitate, it will make the reaction mixture not very clear. As you can see, sodium thiosulfate and nitric acid are clear solutions. However, when sulfur is being produced, when the reaction is happening between these 2 reagents, the solutions become, or the reaction mixture becomes unclear. So, we have the reaction mixture placed on top of a piece of paper marked with an X. So, we are going to measure the time that is taken for the mark X to disappear. This will give us an idea about how long it took to produce a constant amount of sulfur. As we have taken a constant volume, the amount of sulfur that should be present in that volume to create a mixture that makes this X completely disappear will be a constant. So, that is how we measure the constant amount of sulfur that is produced in this reaction. So, to measure the reaction rate, we will have to measure the time that it took to produce this constant amount of sulfur solid. So, now that we have all of this information, let's move on to our first experiment, where we will take 25 cubic centimeters of sodium thiosulfate and we will be mixing 5 cubic centimeters of 3 moles per decimeters cube of nitric acid. So, again, one thing to notice is, as we move along in this practical, we will change the volume of thiosulfate that is taken, in the first part of the practical that is, we will change the volume of thiosulfate that is taken. Initially, we will be taking 25 cubic centimeters of the thiosulfate solution that we initially showed you. So the concentration of the thiosulfate solution that we have here is 0.15 moles per decimeters cube, and nitric acid 3 moles per decimeters cube. So we take 25 cubic centimeters of the sodium thiosulfate solution and mix it with 5 cubic centimeters of nitric acid solution. Overall volume would be 30 cubic centimeters. So now, as this reaction happens, you will see sulfur will be produced, and then we will measure the time for the sulfur precipitate to completely cover the bottom of this reaction mixture. In the next reaction, what we are going to do is we are going to change the number of moles of sodium thiosulfate that is taken into this reaction mixture. How do we do that? We take a smaller volume, or right now we are taking 25 cubic centimeters of sodium thiosulfate. In the next step, we will be taking 20 cubic centimeters of sodium thiosulfate. So the next step after that would decrease the sodium thiosulfate volume to 15 cubic centimeters, and then to 10, and then to 5. So we will gradually decrease the amount of sodium thiosulfate that we take, but if you remember correctly, we have to keep the volume of the overall mixture the same. So you have to remember that the volume of the mixture should be kept the same. So as we decrease the volume of sodium thiosulfate we are taking, we have to add more and more distilled water. So if you decrease the volume of sodium thiosulfate we are taking for this particular part of the experiment, the remainder should be taken, or remainder of the volume should be added with distilled water. So we will be adding distilled water to make up the total volume of the reaction mixture to 30 cubic centimeters. So these are the essential details of the first part of this practical. We will have another part. In this first part of practical, we are going to be observing how the concentration of sodium thiosulfate affect the rate of this particular reaction. So without further ado, let's start our first practical. We have our sodium thiosulfate. We have measured exactly 25.0 cubic centimeters of sodium thiosulfate solution with the help of a burette. So that is present in this beaker here. So let me transfer that amount of sodium thiosulfate into the beaker we have placed on this piece of paper. And since we don't have any water to be added, we don't have to concern ourselves with adding water, because for this very first step, we will not be needing water, because 25 cubic centimeters of sodium thiosulfate and 5 cubic centimeters of nitric acid will make up 30 cubic centimeters. So therefore, there's no need to add distilled water to make the overall volume 30 cubic centimeters. Now, as soon as we add nitric acid, we have to start our stopwatch, because this will give us a good indication as to how long it took for a constant amount of sulfur to be produced through this reaction. So let's add nitric acid. As soon as I add the nitric acid, you will see me turning on our stopwatch. Now, let's wait to see how long it takes for the X mark to disappear. If you observe here, the color is already becoming cloudy. This is due to precipitate being formed, and we can't see X anymore. So this time that you read here is the time that it took for the precipitate to completely disappear due to formation of constant amount of sulfur precipitate. Now we know how we should be carrying out the practical, but before we move on to the next step, let's read the amount of time that it took to completely cover the X mark on this piece of paper. it has taken 20 seconds. So the very first reading that we have here is 20 seconds. Alright students, so now we have come to the second reaction of the first part of this experiment. In the first part, as I mentioned earlier, we will be looking at how the concentration of sodium thiosulfate is going to change the rate of the reaction. So to bring about that change, we have now taken a lower volume of sodium thiosulfate. In the very first reaction, we took 20 cubic centimeters of sodium thiosulfate solution. Now we have here 25 cubic centimeters of sodium thiosulfate. We have kept the nitric acid volume the same. Earlier reaction, we took 5 cubic centimeters of nitric acid. Here also, we have 5 cubic centimeters of nitric acid. Now, if you add these two reactants together, the overall volume would be 25 cubic centimeters. So we should not have varying volumes when we are carrying out this experiment. So to make up for the remainder of the volume, we are adding 5 cubic centimeters of distilled water, so that the overall volume of the reaction mixture ends up being 30 cubic centimeters whenever we are carrying this practical out. So let's take our sodium thiosulfate. There's 20 cubic centimeters here. We'll translate to this main beaker. And before adding our nitric acid, I would like to add the distilled water here, because we need to make sure the overall volume of this reaction mixture is going to be 30 cubic centimeters, as I mentioned earlier. So if you add the nitric acid and then add the water, by that time we have already started the reaction. So we don't want to start the reaction until we have the water in the mixture. So first let's add the water. Now we can add our nitric acid. Keep in mind students, as soon as you add the nitric acid, you have to start your stopwatch. So let's start our stopwatch as we add our nitric acid. As you can see, the reaction has started now. And as soon as the solution turns dark, we will stop the stopwatch. So we stop the stopwatch right when we observe the color, or we observe the cross at the bottom of this reaction mixture disappear. So what was the time that we recorded? We recorded 25 seconds. So the time taken for the cross at the bottom of this reaction mixture to disappear was exactly 25 seconds. Now let's move on to our third reaction of this first part of our experiment. Now, in the third reaction of this first part of our experiment, we are going to mix 15 cubic centimeters of sodium thiosulfate, 5 cubic centimeters of nitric acid, and 10 cubic centimeters of water. So when you mix all of these together, we make 30 cubic centimeters. We are trying to keep the reaction mixture the same volume. So let's add our 15 cubic centimeters of sodium thiosulfate, and then we will add our distilled water. We will add our nitric acid at the end. After adding our distilled water, as a final step, we are going to be adding our 5 cubic centimeters of nitric acid. So as we add 5 cubic centimeters of nitric acid, we have to start the stopwatch. So let's add our 5 cubic centimeters of the nitric acid and start our stopwatch. And now we wait until we do not see the X mark at the bottom anymore. As you can see, due to the formation of sulfur, the solution gets cloudy as it forms more and more sulfur precipitate. So as you can see, we stopped the stopwatch as soon as we could no longer see the sulfur precipitate. Now the reading, so the reading of this stopwatch is 34 seconds. Now let's move on to the fourth reaction. Now we are at the fourth reaction of the first part of our experiment. So in the fourth reaction, we are taking only 10 cubic centimeters of sodium thiosulfate. The volume of nitric solution has not changed so far. We only took 5 cubic centimeters in the first three. And even in the fourth reaction, we are only taking 5 cubic centimeters of nitric acid. And as we want to make the entire reaction mixture have 30 cubic centimeters of volume, we are adding 15 cubic centimeters of distilled water here. So 10 cubic centimeters of sodium thiosulfate, 5 cubic centimeters of nitric acid, and 15 cubic centimeters of water. Now let's add our sodium thiosulfate. And before we add nitric acid, because as soon as we add the nitric acid, reaction will start. So before we add the nitric acid, let's add our distilled water. And finally, let's add our nitric acid. So as before, we have to turn our stopwatch on as soon as we start to add our nitric acid. So let's turn on our stopwatch as we add nitric acid to this mixture. And now we wait until the X at the bottom disappears. As you can see, compared to other previous experiments, it is taking a longer time to get to the observation we want. So as you can see, we have now obtained the observation we want. We can't see the X at the bottom of this beaker anymore, indicating we have produced the amount of sulfur that we aim to produce. So the time that was spent on obtaining this observation was on the stopwatch is 50 seconds. So that means to obtain this observation, we have spent 50 seconds. So after writing it down, now we can move on to the fifth and the final reaction in the first part of this experiment. Now we are at the fifth reaction of the first part of our experiment. In this experiment, we have taken 5 cubic centimeters of sodium thiosulfate solution, 5 cubic centimeters of nitric acid solution, and 20 cubic centimeters of distilled water. So overall, when we add all of them together, the overall volume of the reaction mixture would end up being 30 cubic centimeters, as in the 4 instances before this particular reaction. So let's add our 5 cubic centimeters of sodium thiosulfate, and then we have our distilled water. As always, we don't add nitric acid. Now we add distilled water first, and then at last, or after adding distilled water, as the final step, we add nitric acid. So as we add nitric acid, which we have here, we have 5 cubic centimeters of nitric acid. As soon as we add it, we will be starting our stopwatch. So let's add our nitric acid. There's 5 cubic centimeters here, and we'll start the stopwatch as soon as we add this. So this reaction will happen quite slowly. The reason is we took a very small volume of our sodium thiosulfate solution. So we have the smallest volume of sodium thiosulfate solution taken in our fifth reaction here. So this reaction should take the longest time to give us the observation that we aim to see. As you can see, the reaction is happening. The solution is becoming slightly unclear, but this time the reaction is happening somewhat more slowly. So this is a clear indication that the concentration of the sodium thiosulfate plays a role in the rate of this reaction. Now it's slightly more unclear now, so it will take some time for us to completely not see the X mark. So at that point, we will stop our stopwatch. So at this point, you can see that we can no longer observe the X mark at the bottom, indicating the fact that the reaction has gone to the point that we want it to go. So we have produced a constant amount of sulfur precipitate here. So that is why we can no longer see this X mark. So let's take a look at the time reading. So the time reading is 1 minute and 40 seconds. 1 minute and 40 seconds. This indicates 100 seconds. Now, let's talk about the summary of the first part of our experiment. In the first part of our experiment, what we aimed to see was whether sodium thiosulfate had any impact on the rate of the reaction. To obtain this, we changed the concentration of sodium thiosulfate throughout the reaction mixture. We conducted 5 reactions, and in each of these reactions, we took a different concentration of sodium thiosulfate, and we kept the concentration of nitric acid the same. How we changed the sodium thiosulfate concentration was by taking different volumes of the sodium thiosulfate initial solution we had, which had a concentration of 0.15 moles per decimeters cube, but we started taking smaller and smaller volumes of sodium thiosulfate when we were carrying out different reactions throughout this part 1 of our experiment. And when we were taking different volumes of sodium thiosulfate, we made sure to keep the overall volume of the solution or overall volume of the reaction mixture at 30 cubic centimeters. So the overall volume of the reaction mixture was kept a constant. With all of that information, let's take a look at the time readings. First, our reaction took 20 seconds to give us the observation that we required. And the second reaction took 25 seconds. Third took 34 seconds. Fourth reaction took 50 seconds. And the final reaction that we conducted here took 1 minute and 40 seconds, or in other words, 100 seconds. Now, let's move on to the second part of this experiment. We have nitric acid, and the main focus of the second part of this experiment is to change the concentration of nitric acid in this reaction and observe how the concentration of the nitric acid affects the rate of this reaction. For this purpose, we have measured 5 cubic centimeters of our initial nitric acid solution. The concentration of the initial solution was 3 moles per decimeters cube. And then we have sodium thiosulfate solution, which has a concentration of 0.15 moles per decimeters cube. We have taken 25 cubic centimeters of it. So 5 cubic centimeters of nitric acid is going to be added to 25 cubic centimeters of thiosulfate solution. Like in the previous experiment, the overall reaction mixture will have a volume of 30 cubic centimeters. Since these two solutions together will make up for 30 cubic centimeters, we do not have to add any distilled water. So, since we have already measured exactly 5 cubic centimeters of nitric acid, we are going to place it here, as transferring it is not necessary. We can actually place it here in our X mark or on the X mark, and we will be adding our sodium thiosulfate to this directly. So as before, we have to make sure the stopwatch is starting from 0, and then as soon as we add our sodium thiosulfate to this nitric acid that we have here, we will start the stopwatch. So let's add our sodium thiosulfate solution here. And we can see the reaction starting to happen. So as soon as we are not able to see the X mark at the bottom of this beaker, we stopped the stopwatch. And the time reading is 20 seconds. So we have 20 seconds on the clock, meaning the time taken for the X mark to disappear was 20 seconds. Now, this was the very first reaction of the second part of our experiment. Let's move on to the next reaction. We have a total of 5 reactions in the second experiment as well. So let's move on to the second reaction of the second part of this experiment. Now students, we are here at the second part of our experiment. In this second part of our experiment, we are going to be looking at how the concentration of nitric acid affects the rate of this particular reaction. So in the earlier first part of our experiment, we looked at how thiosulfate concentration affected the rate of the reaction. So we changed the volume of the thiosulfate that was taken in each of the 5 reactions. But in this second part of our reaction, we will be focusing on changing the volume of the nitric acid we take. So 4 cubic centimeters of nitric acid, and the amount of sodium thiosulfate we take will not change. We have taken 25 cubic centimeters of sodium thiosulfate. So throughout the second part of this experiment, we will be taking only 25 cubic centimeters of sodium thiosulfate. And so since we only have 4 cubic centimeters of nitric acid, to make up the total solution to be 30 cubic centimeters, we have to add 1 cubic centimeters of water as well. So we have 1 cubic centimeters of water measured out here. So let's start with nitric acid. So we'll take this beaker and we'll place it here. Now this has 4 cubic centimeters of nitric acid. To that we will add our distilled water. After adding the distilled water only, we will be adding our sodium thiosulfate. As we all know, as soon as the sodium thiosulfate is added, we have to make sure the stopwatch is going to be turned on. So right now it is not zeroed in, so let's zero in our stopwatch. And then we'll move on to add our sodium thiosulfate. In this beaker, we have 4 cubic centimeters of nitric acid along with 1 cubic centimeters of water. Overall volume here is 5 cubic centimeters. And we are adding 25 cubic centimeters of sodium thiosulfate. So when we add this 25 cubic centimeters of sodium thiosulfate, overall volume will be 30 cubic centimeters. You have to keep that in mind as well. So as soon as we add it, we will be turning on our stopwatch. Now we will wait until we can no longer see the X mark. As you can see, we stopped the stopwatch exactly when the X mark could no longer be seen. Let's take a look at the stopwatch reading. So the time recorded on the stopwatch is 20 seconds. So it took exactly 20 seconds to observe the same observation we observed in the very first reaction of this part 2 of our experiment. So in the second experiment also, the time taken for the same observation to take place was 20 seconds. With that in mind, let's move on to our third reaction. On this third reaction of our experiment, we are going to take 3 cubic centimeters of nitric acid, 25 cubic centimeters of sodium thiosulfate, and 2 cubic centimeters of water. Overall, we have 30 cubic centimeters of reaction mixture here. So when it comes to the nitric acid we have here, in the third reaction we have taken a lower volume of nitric acid compared to the previous 2 reactions. The very first reaction, we took 5 cubic centimeters of nitric acid, second one 4 cubic centimeters of nitric acid, and in our third reaction we have taken 3 cubic centimeters of nitric acid. And to this nitric acid volume, we are going to be adding 2 cubic centimeters of water. And then finally, we will be adding our 25 cubic centimeters of sodium thiosulfate. And as before, when we are adding the sodium thiosulfate, we have to make sure to turn on our stopwatch. So let's take our sodium thiosulfate, and as we add the sodium thiosulfate to our nitric acid, we have to start our stopwatch. So now we can see the reaction has started to happen. Solution is becoming a little bit unclear. And you can see now we can no longer see the X mark at the bottom of the beaker. The time that is recorded in the stopwatch is 20.5 seconds. 20.5 seconds. This is in line with the observations that we made earlier. The first time that the reaction took place, or in the first reaction that we conducted under part 2 of this experiment, we saw it took 20 seconds to bring about this observation. And then the second reaction took 20 seconds again. In the third reaction, it is more or less the same, 20.5 seconds, 0.5 second of a difference. So now, let's move on to the fourth reaction. Now students, we have the fourth reaction of the second part of our experiment. So in this fourth reaction, we have taken 2 cubic centimeters of nitric acid, 25 cubic centimeters of sodium thiosulfate, and 3 cubic centimeters of water. So first let's take our 2 cubic centimeters of nitric acid here, and to that, as in the instances before, we are going to add the distilled water. So we have 3 cubic centimeters of distilled water here. We have transferred it into this main beaker here, and finally we are adding our sodium thiosulfate. So before adding our sodium thiosulfate, make sure the stopwatch is reading 0, and then we will add our sodium thiosulfate. As before, when we are adding the sodium thiosulfate, we will be starting our stopwatch here. As you can see here, I'll be starting the stopwatch when I'm adding sodium thiosulfate. The stopwatch has started and the reaction has started as well. You can see the color of the solution becoming unclear. You can see at this point, we can see we no longer can observe the X at the bottom of this beaker. Let's take a look at how long it took to come to this observation. This observation was observed exactly at 20 seconds. Now, let's move on to our fifth and final reaction for this part of our experiment. Now, we are at the final reaction for this second part of our experiment. We have taken 1 cubic centimeters of our nitric acid solution, and then we have not changed our sodium thiosulfate solution volume here. We have taken 25 cubic centimeters of it, and we have taken 4 cubic centimeters of our distilled water. So let's take our nitric acid, 1 cubic centimeters of nitric acid here, and let's add our 4 cubic centimeters of distilled water. And finally, we have our sodium thiosulfate. Now, as before, when we are adding the sodium thiosulfate, we will have to turn on our stopwatch. And before turning it on, please make sure to always see if the stopwatch is starting from 0. Now, since it is starting from 0, we can move on to add sodium thiosulfate. Now we can see the reaction has started. Now we will wait until we can no longer see the X mark in this beaker. So at this point, you can observe that we can no longer see the X mark at the bottom of the beaker. Let's take a look at the time. The stopwatch reads 21 seconds. So for us to obtain the same observation that we observed in the first 4 reactions of this part, it has taken 21 seconds. So if you go over the observations that we made on the second part of this experiment, we can note that in the very first reaction of the second part of our experiment, we took 5 cubic centimeters of nitric acid, and the second reaction had 4 cubic centimeters of nitric acid, third one had 3, fourth one had 2, and the last reaction had only 1 cubic centimeters of nitric acid. Everything else remained a constant. The overall volume we kept a constant, as well as the sodium thiosulfate concentration was kept a constant. However, our main goal was to observe how long it took for us to obtain the same observation, which is not being able to see the X mark at the bottom of the beaker. In the first reaction, it took 20 seconds. In the second reaction also, it took 20 seconds. Third one, it took 20.5 seconds. Fourth one, 20 seconds. And the fifth one, we can see it has taken 21 seconds. So with that observation, we can conclude our experiment here. And these are just the observations that we gather in our lab. Based on these observations in the lab, we can calculate the rate of the reaction, order of reaction with respect to each of the reactants we had here, and we can write an overall rate equation for this reaction based on the observations we made in the lab. So let's move on to those calculations and some questions revolving around this practical. Now students, we have learned about the theory parts revolving around experiment number 31. We conducted the experiment in the lab, and here we are going to now do some questions that are revolving around experiment number 31. So let's take a look at the first question here. A series of tests to measure the order of the reaction. A series of tests to measure the order of the reaction was carried out using 0.16 moles per decimeters cube concentrated sodium thiosulfate and 3.0 moles per decimeters cube concentrated HCl. The volumes of the reactants used are indicated in the table below. The reactions were carried out at 300 Kelvin temperature. So that means we don't have to worry about the temperature because all of these reactions were carried out at the same exact temperature. So the temperature was kept a constant. To keep the volume of the reaction mixtures a constant, water was added. The time taken for constant amount of sulfur to be produced was measured. Now students, there are two things that are mentioned here. One thing is when you are mixing these different solutions, if you are trying to change the concentration of each of these reactants, then you have to change the volumes of each of the reactants we take into the reaction mixture. So if you change the volumes of these reactants that we take into the reaction mixture, at that point the overall volume will change. If you want to keep the overall volume a constant, then we will have to add water for the remainder of the volume. So students, we can see here we have changed the volume of sodium thiosulfate in this section, and while we do that, we have added water to make sure the overall volume remains the same. Here in this section, we have changed the volume of HCl we take into this reaction mixture. To make sure the overall volume remains the same, we have added water. Alright, so in this experiment, we are going to measure the time taken for a constant amount of sulfur to be produced. And we know how to measure the time for a constant amount of sulfur to be produced. We explained that in the experiment as well as in the lab. So now over here, we can see that in this part of our experiment, we are changing up until the step number 4, we are actually changing the concentration of sodium thiosulfate while keeping the HCl concentration the same. And we can say again, including the step 4, we can say again, including the step 4, when you're going from step 4 to step 7, you can see we are keeping the sodium thiosulfate concentration the same while decreasing the concentration of HCl. Now I keep using the word concentration, that is because when you add different volumes of a reactant while keeping the overall volume of the reaction mixture the same, what happens is the changing of its concentration, right? So the overall volume of this reaction mixture happens to be in each of these cases 30 milliliters. But in 30 milliliters in this reaction mixture 4, we have only 5 cubic centimeters of the original HCl solution. and then it has gone down to 4 in the next reaction, and 3, and then 2. So by changing the volume of the specific reactant, we have changed the concentration of that reactant in that reaction mixture. Let's move on to the first question. When the acid concentration of the reaction mixture is a constant, when we keep the acid a constant, the reaction rate can be expressed as follows. If the acid concentration is a constant, we can say the rate is proportional to the sodium thiosulfate raised to the power m. M will be the order of the reaction with respect to sodium thiosulfate. When the thiosulfate concentration of the reaction mixture is a constant, the reaction rate can be expressed as follows. We can say rate is proportional to HCl concentration to the power n. N will be the order of the reaction with respect to HCl. Using the given information, calculate the values of m and n. Let's do that. So let's start with sodium thiosulfate. Let's talk about sodium thiosulfate here, right? Na2S2O3. So order of the reaction with respect to sodium thiosulfate is m. If you wish to find that, we have to first take a look at this table here, and we have to choose 2 tests that are carried out at 2 different concentrations or 2 different volumes of sodium thiosulfate, and we can take a look at their rates as well. So if you want to take 2 volumes that are easier to work with, you can take volumes such as 1520 or 2025, right? Because we are going to first write an expression, and then afterwards we are going to be writing, we are going to carry out a division between these expressions, right? So first of all, we will move on to this part over here. We have been given an expression that when the acid concentration is a constant, in this question they say rate is proportional to sodium thiosulfate concentration in Na2S2O3 concentration raised to the power m. We can also use a rate or different type of a constant here. Let's say K1, we can use a constant here because here there's a proportionality. If you want to make it an equation, we can include a constant here. So now R can be made equal to K1 multiplied by sodium thiosulfate concentration raised to the power m. Now, since we know that the concentration of sodium thiosulfate in the series of tests that we carried out depended on the volume of sodium thiosulfate we used, we can say that the concentration of sodium thiosulfate concentration is directly proportional to the volume of sodium thiosulfate we used. So we can also rearrange this equation in the following manner. We can also write the rate is proportional to the volume of sodium thiosulfate raised to the power m, because in the concentrations place we can write volume. So actually in that case you don't need to write square brackets, we can just write volume to the power m, right? So we can write, since we have a proportionality here, we can write it is equal to K, we can write K dash or K1 if you wish here, into volume raised to the power m. Right. So we can now move on to substituting the values. Now, if you are someone who would wish to calculate the actual concentrations for each of these solutions, you can go ahead and do that. That is also not a problem. But we can calculate the rate of the reaction with the use of volumes as well. So just so that you know. So if you are someone who would like to work with concentrations, we can go ahead and do that. We can take the reaction number 1 and 2 and then find the concentration of sodium thiosulfate in the reaction mixture. So original solution's concentration is 0.16, right? Original sodium thiosulfate concentration is Na2S2O3 concentration is 0.16 moles per decimeters cube. For the time being, we can write it down as M. So for test 1 or reaction 1, the overall volume of sodium thiosulfate that was taken was 12 cubic centimeters. Yes, 12 cubic centimeters, right? Cubic centimeters. So if you want to convert it into number of moles, we can take 12 cubic centimeters, multiply by the concentration 0.16 moles per decimeters cube, and we have to divide it by 1000, right? Because 12 cubic centimeters should be converted into cubic decimeters. And this overall value should be divided by the overall volume of the reaction mixture. So the overall volume of the reaction mixture happens to be 30 cubic centimeters, right? So 30 cubic centimeters, when you want to convert it into cubic decimeters, you need to divide this by 1000. So division by 1000 can be written up here like so. So you can very clearly see that these cancel off, right? This gives us the concentration in moles per decimeters cube. And we can see 12 here, 30 here, there are 5 6s here, and there's 2 over here. So the concentration can be written as 0.32 divided by 5 moles per decimeters cube. This is the concentration of the test 1's sodium thiosulfate. So sodium thiosulfate concentration in test 1 is this. We can work with this concentration, and in test 2, the concentration of sodium thiosulfate would be 15 cubic centimeters, or we take 15 cubic centimeters of the original solution. So we can write 15 cubic centimeters divided by 1000. You convert it into decimeters cube. You multiply it with its original concentration, which is 0.16 cubic centimeters. Now the number of moles of sodium thiosulfate that we have taken is calculated here. If you divide this value by overall volume of the reaction mixture, which is 30 cubic centimeters, you get to the concentration. But this 30 volume is in cubic centimeters. If you want to convert it into decimeters cube, you have to multiply, actually you have to divide cubic centimeters by 1000, right? So when you do that, the 1000 comes up here, and when you do that, you will see that these will cancel off. There will be 1 here and there will be 2 here. So the concentration here happens to be 0.08 moles per decimeters cube. 0.08 moles per decimeters cube. So these are the concentrations that we get. Now, if you wish to further solve this and get to a numerical value, we can do that. We can solve this part separately, and we can write 0.064 moles per decimeters cube, because that's what happens when you divide this number by 5, right? So 0.064 and over here what you have is 0.08 moles per decimeters cube. So the concentration has increased slightly. So now we have obtained the concentrations of the test 1 or reaction mixture 1 and reaction mixture 2. We know the sodium thiosulfate concentrations. And if you want to take a look at the time it took, we can see the first reaction took 21 seconds, the second reaction took less time than that. So we do know, since we take rate as the amount of change, divided by time, since we know the amount of change is the constant amount of sulfur that is produced, we can say that rate is going to be equal to a constant value of sulfur that is produced. So we can say it's a constant. So I have denoted that with a K, and that constant change should be divided by T. So we can also say rate of the reaction is proportional to 1 over T. Rate of reaction is proportional to 1 over T. So in that case, students, we can write that rate is equal to, we know, rate constant multiplied by sodium thiosulfate concentration into the power m. So if you substitute these values that we know about over here, for the reaction 1, the rate is going to be 1 over, right? We can actually write this, if you want, in the following way. If you call this rate constant K, we can call that rate is equal to K dash 1 over T, K dash 1 over T, right? So let's say rate is equal to, when it comes to experiment 1, rate is equal to K dash divided by 21 seconds. K dash divided by 21 seconds is equal to rate constant multiplied by Na2S2O3. So Na2S2O3 concentration, do we know already? Did we find it? Yes, we found this value, and that happens to be 0.064 moles per decimeters cube. So for the time being, we'll just write down the numerical value. It will be easier to work with it. So let's take this as our expression 1. And then in the second test, also we have the rate still equal to K dash divided by time. So let's take K dash divided by time as the rate. So second test used 16.6 seconds. 16.6 seconds was the time that was spent to observe the same observation. It is equal to K multiplied by the concentration of sodium thiosulfate to the power m, and this is our second statement. Now we have few unknowns here, K dash and K we don't know. So the best way to get or remove them from these expressions is to divide them. Right. Let's divide expression 2 by expression 1. So we can write, we are going to divide expression 2 by expression 1. So at that point, we will have 21 divided by 16.6 is going to be equal to 0.08 divided by 0.064, but you can't forget about the power m. power m. Right. So when you do that, if you further solve it, you'll get to the following answers. So when you divide 21 from 16.6, it's going to be around 1.26, and over here when you divide this, it's going to be 1.25. We can't forget the power m here. So 1.26 and 1.25 are similar values, so there can be slight errors in measuring these times. However, these two values are quite similar. So what should be the power over here, or what should be the value of m over here for these two values to be the same? If the power is 0 here, that means whatever the number to the power 0 is 1. However, this is not going to be applicable here because these two values over here, 1.25 and 1.26, are very similar to one another. So that means the power should be 1. If 1.25 to the power 1 is written, then this could be true. So therefore, m, the value of m is 1. So that means order of reaction with respect to sodium thiosulfate is equal to 1. Order of the reaction with respect to sodium thiosulfate is equal to 1. And they also ask for the order of the reaction with respect to HCl. Now you can see here from reaction 4 onwards, the only thing that we have changed here is the volume of nitric acid, HCl, that we have used here. Not nitric, we have used HCl. So only thing we have changed here is the volume of HCl here. We have kept the sodium thiosulfate volume a constant. So students, from the reaction 4 onwards all the way up to 7, we have changed only one reactant's concentration. And as we change HCl's concentration, do you see a change in the time that it takes to produce a constant amount of sulfur? No. So there by itself, you should get the idea that concentration of HCl has had no part in determining the rate of the reaction. That means the order of the reaction with respect to HCl is 0. Order of the reaction with respect to HCl is 0. Now if you use the volume method over here, right? Now initially we use the concentration method to get to the order. So we know that we can say that the rate of the reaction is equal to a constant multiplied by volume of the HCl that we used in this experiment to the power n, because we know volume was the way that we control the concentration of HCl in the initial reaction mixture. As we decrease the volume of HCl added to the reaction mixture, the concentration of HCl changed. So the concentration of HCl in the reaction mixture was proportional to the volume of HCl that we added to the reaction mixture. Right, and we know R is equal to, let's say, K dash 1 over T, or K dash divided by T. Using these equations, we can write an expression for the rate constant, or expression for the rate of the reaction for reaction 4 and 5. So we'll take reaction 4 and 5 and find out the order of the reaction with respect to HCl. So here we have 5 and 4 cubic centimeters, and the time that it took was 10 and 10.1. Right. So we can now write rate, or in this case K dash for reaction number 5. K dash divided by time, which is 10.0 seconds, is equal to a constant multiplied by volume of HCl that was taken into this particular experiment. In this case, we took 5 cubic centimeters to the power n. So let's call this expression number 1. And in the, I think this was for the 4th reaction, right? For the 5th reaction, I initially wanted to take the 4th reaction, so we'll erase this. For the reaction number 4. For the reaction number 5, we can write another expression, K dash divided by 10.1 is equal to, we have taken at that point 4 cubic centimeters of HCl, so the volume will be 4 here, and that is going to be your expression 2. Again, we have quite a few unknowns here. To remove them, we can divide one expression from the other. However, students, when you're dividing these values, divide the expression with the larger values with the expression with the smaller values. So we can divide expression number 1 with expression number 2. So when you do that, we can see these k's and k dashes cancel off. So expression number 1 is going to leave behind 10.0 here, and on top it is going to leave behind 5 to the power n. I will include the power n separately later on. And expression number 5 is going to leave behind 10.1 on top here, because we are dividing 10.0 by this particular part of the expression. So then the denominator comes on top, and it is going to leave behind 4 as well. So we can't forget the power n. So according to this, so when you divide 10.1 by 10, it's still 1.01, very close to 1. It is equal to 5 divided by 4 to the power n. Now 5 divided by 4 is basically, students, 1.25. 5 divided by 4 is 1.25. 1.25 to the power n. So students, we can now see that 1.25 to the power n should be equal to 1.01. So let's say 1.01 is more or less close to 1. You can see if 1.25 had a power of 1, if n was equal to 1, then the answer over here should be very close to 1.25. Because we know when you're measuring time, there can be small mistakes that you make. So therefore, these values are not going to be absolutely accurate. So there can be small deviations from the value that we see over here. That's all right. So this particular value that you see over here is not close to 1.25. So n can't be 1. However, if n was 0, any number to the power 0 is 1. And this 1.01 is basically very close to 1, right? 1.00, let's say. So that means, what is the value of n? N's value is 0. If n was 0 only, you will be getting this answer. So therefore, students, we can write order of the reaction. Order of reaction with respect to HCl was 0. Order of the reaction with respect to HCl was 0. So students, we have found out both the order of the reaction with respect to sodium thiosulfate, and then we have found out the order of the reaction with respect to HCl. Write the balanced chemical equation for the reaction between sodium thiosulfate and HCl. So sodium thiosulfate we can write Na2S2O3 reacting with HCl will produce sodium chloride, sulfur, sulfur dioxide and water. Now you can also include the state symbols here. Sodium chloride is present as an aqueous solution, so is HCl, and sodium chloride will be produced as an aqueous solution, whereas sulfur will be a precipitate. And that is the observation that we are trying to observe, the formation of a milky precipitate. And then we have sulfur dioxide produced as a gas, but it can dissolve in water to form aqueous solution, or we can write in the reaction it is produced as a gas also, right? And then liquid water will be produced. So this reaction is not balanced. So to balance it off, we have to first start with the fact that sodium, on the left hand side there are 2 sodiums, right hand side there is only 1, so we can add a 2 here. When you do that, the chlorine number changes on the right hand side. To balance it, we can add a 2 here, and you can see the hydrogens then automatically will be balanced. The rest of the atoms or elements are completely balanced. So this is the balanced chemical equation for the reaction between HCl and sodium thiosulfate. Now students, in this part of the question, they are asking us if the concentration of solid sulfur formed is 0.01 moles per decimeters cube, calculate the fraction of sodium thiosulfate that has reacted by the time 12.5 seconds has passed, and consider the third reaction mixture to answer this question. So let's move on to the table here. So this is our third reaction mixture. We are using 20 cubic centimeters of sodium thiosulfate, 5 HCl, and the time is 12.5. And we know sodium thiosulfate concentration is 0.16 moles per decimeters cube. Now they are asking us to initially find the fraction. So that means we need to have an idea about the initial number of moles of sodium thiosulfate that was present in the medium. So just to give you an idea, we have an overall 30 cubic centimeter or 30 milliliter volume reaction mixture, and within this 30 milliliters we have, according to the third reaction mixture, we have 20 cubic centimeters of sodium thiosulfate, 5 HCl and 5 water. 20 cubic centimeters of sodium thiosulfate would be there. So we have to write 20 cubic centimeters of sodium thiosulfate will be there. So our main concern is sodium thiosulfate, so therefore we will write that down. And the other 2 components are 5 cubic centimeters water and 5 HCl. And the concentration of the sodium thiosulfate here happens to be 0.16 moles per decimeters cube. That is the concentration of sodium thiosulfate. So if that is the concentration, if we double check the concentration because we don't want to move ahead with the wrong value, 0.16 moles per decimeters cube sodium thiosulfate concentration was the concentration we have used. So after writing that down, we can now calculate the initial number of moles. We can write initial sodium thiosulfate amount. Initial sodium thiosulfate amount is equal to its concentration 0.16 moles per decimeters cube multiplied by its volume. The volume of this particular solution that we used was 20 cubic centimeters. So 20 cubic centimeters mean 20 divided by 1000 so that we have it in decimeters cube. So you can see decimeters cube and per decimeters cube cancel off, and we can write this answer as, we can see 20 multiplied by 16 is going to be 3.2 divided by 1000. This many moles were there initially. This is the initial number of moles. And then they say within this 30 cubic centimeter volume, the overall reaction mixture added up to 30 cubic centimeters, right? 30 cubic centimeters. In this 30 milliliters or 30 cubic centimeter volume, the amount of sulfur that got formed in order to completely make the X mark disappear that was at the bottom of the beaker, in order to completely disappear the X mark that was at the bottom of the beaker, the concentration of sulfur that got produced was 0.01 moles per decimeters cube. So we can now calculate the amount of sulfur that was present at that point. We can write the amount. Now, in order to produce this amount of sulfur, 12.5 seconds were passed. So basically, they're asking us at the time at which we have passed 12.5 seconds, how much of sodium thiosulfate has gotten reacted, and we have to communicate that information as a fraction. So the amount of sodium thiosulfate, the amount of sulfur that was produced by 12.5 seconds, or when 12.5 seconds has passed, is equal to the concentration of sulfur that was observed at that point. According to the question, that was 0.01 moles per decimeters cube, and the overall reaction mixture's volume is 30 cubic centimeters. So if you want to convert it into decimeters cube, you can divide by 1000. So this is going to be 30 cubic centimeters. So the answer would be at that point 0.3 divided by 1000, this many moles, right? So you can see decimeters cube and per decimeters cube cancel off, leaving behind only moles. So this is the amount or the number of moles of sulfur that was produced when 12.5 seconds has elapsed, right? So we need to find out by that time to produce this amount of sulfur. So according to the previous question, we know that sodium thiosulfate, sodium thiosulfate to sulfur solid ratio is 1:1. So this is not 2, this is 1. So 1:1. The ratio is 1:1. So that means we can write according to the reaction ratio, we can write according to reaction ratio, amount of sodium thiosulfate that got reacted is going to be equal to the same number of moles of sulfur that got produced, because sulfur to sodium thiosulfate ratio was 1:1. So if this amount of sulfur was produced, that means the amount of sodium thiosulfate that got reacted within the same duration of time was equal to the amount of sulfur that got produced. So 0.3 divided by 1000 would be the answer. This is the number of moles of sodium thiosulfate that got reacted. So we have calculated the initial number of moles of sodium thiosulfate. So, and we know now the amount of sodium thiosulfate that got reacted. So therefore we can write the fraction of Na2S2O3 that reacted within 12.5 seconds. This is equal to the number of moles of sodium thiosulfate that reacted, which happens to be 0.3 divided by 1000, this many moles, and then divided by the initial number of moles of sodium thiosulfate. So the initial sodium thiosulfate amount is 3.2 divided by 1000 moles. So initial number of moles was 3.2 divided by 1000 moles. So you can see thousands cancel off. It will be 0.3 to 3.2 as a ratio. But if you want to keep it as whole numbers, we can keep 3/32. So this is the fraction. This is a fraction of sodium thiosulfate that reacted within 12.5 seconds. So this is the answer to the question that was asked. We can now move on to the next question. If the same reaction was conducted at a higher temperature, will the reaction happen at a faster rate or the same rate? Briefly explain with reasons. Now students, in the theory part of our experiment, we explained when you increase the temperature of a reaction mixture, you provide energy to the particles in the reaction mixture. So when the reactant particles gain more energy, they will have higher kinetic energy and their movements will be faster. So therefore their collision rates per second or per unit time will be higher. And when they have higher amount of collisions, as well as each particle now has a higher amount of energy. So we also discussed that the total number of particles that surpass the required activation energy value will also be higher, right? So that means the number of particles within the system that can have successful collisions will be higher. And now a successful collision has a few requirements. The first requirement would be collisions happening, or we can also say collisions happening in the right orientations. And apart from that, each of the particles that are colliding with the right orientation should have a sufficient amount of energy for it to turn into products. If you don't meet the minimum energy requirement for the reactants to turn into products, then even though you have a correct oriented collision, you will not have a product. Even though the reactants are correctly oriented, and when they collide, if they don't have the sufficient amount of energy to turn into products, they will not turn into products. So students, when you provide energy to a system, what happens is due to the increased average energy of the entire number of particles within the system, the number of particles that surpass the activation energy barrier will increase. So the number of particles that can take part in successful collisions will increase. Apart from that, the frequency of collisions overall both successful and unsuccessful collisions, the frequency of these collisions will increase. So due to this, the rate of the reaction will increase. So when you are writing your answer, make sure to include the overall energy increase of the particles of the system when you provide a higher temperature. And due to the increase of energy in the particles of the system, the fraction of particles that can surpass the activation energy barrier will also increase. And due to this reason, the number of collisions, successful collisions that take place within a unit time will increase, or we can say the frequency of successful collisions will increase, leading to a higher rate of the reaction. So that will be the answer to this question here. And the second question, write the balanced equation for the reaction between thiosulfate and H+. Thiosulfate and H+. Now we learnt this in the theory part. When thiosulfate ions are added with H+, you get these products. You will get solid sulfur, sulfur dioxide, and water. Solid sulfur, sulfur dioxide, and water. And to balance this reaction, you'll have to add a 2 in front, and we'll write the state symbols as well. Now, just to remind you, we will write down what happens if you add H+ to sulfite, right? If you add a strong acid to sulfite ions, you will see the formation of sulfur dioxide and water. So why we do learn this is because at this point it will be clear to you that to identify the thiosulfate ion, we can add an acid to it. So at that point it will produce a sulfur precipitate, and when sulfur precipitate gets formed in the aqueous mixture, the mixture will turn milky in color, and the sulfur precipitate will have a yellowish hue to the precipitate, and apart from that, a pungent smelling gas will be produced, and that happens to be sulfur dioxide. But if you carry out the same reaction, or if you add H+ to sulfite ion solution, you will produce sulfur dioxide and water only. So the only observation would be the noticing of a pungent smelling gas. So the pungent smelling gas that is produced here is sulfur dioxide. For the above reaction, order of the reaction with respect to thiosulfate ion is 1, and the order of the reaction with respect to H+ is 0. What is meant by this statement? So students, what this statement means is that when you are writing the rate expression, we do not have to include the H+ concentration. Instead, the rate of the reaction depends on mainly the concentration of the thiosulfate ions, right? So we usually don't include the 1 here because we know when there is nothing written there, the power of that is going to be 1. And this actually states that this reaction that we are talking about is not an elementary reaction. In an elementary reaction, both of the reactants will influence the rate of the reaction, and their orders would be the stoichiometric coefficients you see in their balanced chemical equation. So this is very clearly not a elementary reaction, and you can also understand that this is a multi-step reaction. So students, in a multi-step reaction, the reaction is going to be happening in mainly 2 steps. We can just roughly draw a sketch like so, right? So in step 1, right, let's say the activation energy of step 1, like we have written this earlier in the theory parts as well. So this is the activation energy 1, and over here we have activation energy 2. So this energy diagram, reaction progression is on the x-axis. So in the energy diagram, you can see the first step of this reaction has a higher activation energy. So when it comes to reactions, if it has a high activation energy, those type of reactions usually happen very slowly. And reactions with small activation energies usually happen faster. So when you observe the rate equation, you know only the concentration of sodium thiosulfate has influenced the rate of the reaction. That indicates that the slow reaction included sodium thiosulfate, or thiosulfate ion. So based on the statement above, we can understand that there were couple of steps in this reaction. So this is not an elementary reaction, it's a multi-step reaction. And in the multi-step reaction, the slow reaction determines the rate of the reaction. That means in this multi-step reaction, the slowest step included thiosulfate ions. So thiosulfate ions were included in the slower step of the reaction, and usually students, the slower step has a high activation energy. So that is what this statement actually would mean. So you can write down that based on this we can understand that there is no influence that comes from the concentration of H+, leading to the conclusion that this particular reaction is not an elementary reaction. And then you can also write this rate equation indicating this is the rate expression for the following reaction. And also you can communicate the fact that this is a multi-step reaction, and in the multi-step reaction, the slowest step determines the rate, and in this case, the slowest step is going to be including thiosulfate ion. Let's take a look at the third part of this reaction. If the rate of the reaction mentioned above is R, write the rate expression or expression for R. So at that point, like we have mentioned in the previous answer, rate would be equal to rate constant multiplied by the thiosulfate ion, S2O3 2 minus, to the power 1, and multiplied by our H plus concentration. Now we know the H plus concentration has a power of 0. This has a power of 1. We usually don't write the power 1 here. But in this case, just to give you an idea about what we are dealing with, I will write it here. So whenever something has a power of 0, that means the overall value of that thing is 1. Any number to the power 0 is equal to 1. So the overall rate expression that you can write is this: S2O3 2 minus. This is going to be your overall rate expression. So that is the answer to this question. Now we move on to the third question. For a reaction between X and Y, the initial concentrations and the rates are given in the table below. Initial concentration and the rates. We can see the initial concentrations of X and Y, and the initial rates are given in the table. What is the order of the reaction with respect to X? Now students, when you are trying to find out the order of the reaction with respect to any reactant, the best way to do the question, like a question like this, is by taking a look at the reactions and picking two reactions where the Y reactant's concentration has remained a constant, so that only variation we see in the two reactions are the X reactant's concentration. So you can see reactant 1 and reactant 2, reaction 1 or test 1 and test 2, we have the concentration of Y reactant a constant. The only thing that has changed is the concentration of X reactant, right? So at that point, we have the rates of the reactions as well. So let's say you write an expression like this. You write an expression for the order of the reaction. R is equal to rate constant multiplied by X concentration to the power m, that is the order of the reaction with respect to X, and Y concentration to the power n, that is the order of the reaction with respect to Y. So for the first reaction, reaction number 1, right, test 1. For the test 1, let's write an expression. So we know for the test 1, the rate is given as 1.0 into 10 to the power minus 2 moles per decimeters cube per second, and it is equal to rate constant, which we don't know, multiplied by concentration of X, which happens to be 0.25 moles per decimeters cube, multiplied by concentration of Y, again 0.25 moles per decimeters cube. And we shouldn't forget their orders as well. Now X has an order of m, Y has an order of n. So let's say this is the statement 1 or expression 1. Then for test 2, we can write another expression. Right, we know the rate equation is this, so we will substitute the values that we see in the test 2. So the order is, the rate of the reaction is 4.0, order of the reaction is 4.0 into 10 to the power minus 2 moles per decimeters cube per second, which is equal to rate constant, which we don't know, and concentration of X at that point is 0.5, so we have double the concentration of X, right, 0.5 moles per decimeters cube per second, actually moles per decimeters cube. In this case we are talking about concentration raised to the power m, and the concentration of Y hasn't changed, it's still 0.25. Here it's 0.25, here also it is 0.25 moles per decimeters cube raised to the power n. Let's call that expression 2. So you might see in both these expressions there are things that we don't know. For example, we don't know m, we don't know n, and we don't know this rate constant k. But if you actually divide expression 2 by 1, the reason why I divided expression 2 by 1 is because expression 2 has a greater rate. So when you divide expression 2 by 1, you will get to a larger number rather than a fractional number. So we want to make it easier for ourselves when you are solving a question like this. So always divide the larger number by the smaller number. A small number should be used to divide the larger number. So here we have the rate 4.0. So I will, since the units get cancelled off, I will leave the units out here. So 4.0 into 10 to the power minus 2 divided by 1.0 into 10 to the power minus 2. These are the rates. And we know when you are dividing these rate constants, they will also get cancelled off. Just to show you that it is cancelling off, I will include them here. And the concentration of X was in the second reaction it was 0.5 to the power m. Here it is 0.25 to the power n, and here it is 0.25 to the power m, and Y's concentration is 0.25 to the power n again. So we can very clearly see that these two are identical. We can cancel them off. They have the same number as well as the same power, so we can cancel them off. And rate constants can be cancelled off. 10 to the power minus 2 can be cancelled off. So the answer over here is going to be 4, because 4.0 divided by 1 is equal to 4 is equal to, now when you solve 0.5 and 0.25, since they have the same order, we can bring them to the same bracket and write 0.5 divided by 0.25. So when you solve this, when you cancel them out, that is going to be 2. So 4 is equal to 2 to the power m. 4 is equal to 2 to the power m. And therefore, this can be written like this as well. M is equal to, at that point, 2. M is equal to, at that point, M is equal to 2. So in this particular reaction that we were carrying out, we were talking about X and Y. So what is the order of the reaction with respect to M, as we found out over here? So with respect to X, the order of the reaction. With respect to X, the order of the reaction is M. So M's value is 2. So that means order of the reaction with respect to X is equal to 1. Not 1. With respect to X is equal to 2. Order of the reaction with respect to X is equal to 2. Right, students. So now we have found out order of the reaction with respect to X. And the second question is, what is the order of the reaction with respect to Y? Again, we will have to follow the same steps, but for Y. We have over here 2 tests that are done while keeping the concentration of X a constant. Concentration of X was kept a constant, and we can observe the concentration of Y has changed. So students, you should be able to say the order of the reaction with respect to Y without having to do a calculation, but when you're answering the question you have to show the calculation. But you should be able to, in your head, calculate the order of the reaction with respect to Y. You can see here that X concentration has been kept a constant when it comes to the test 2 and test 3. So the impact that it has on the order of the reaction will not be considered. So since they have the same constant concentration, only variation that has happened here is Y. So that means whatever the change that takes place in the rate of the reaction is due to the variation that we saw in the concentration of Y, because we kept the concentration of X a constant. So when you double the concentration of Y, we can see that the rate has doubled. When you double the concentration of Y, the rate has doubled. So this relationship is seen in first order reactions. When you double the concentration, rate will double. In second order reactions, when you double the concentration, the rate will quadruple. We saw here when it comes to the X concentrations, while keeping the Y concentrations the same, when you double the concentration of X, the rate was quadrupled. Rate was multiplied by 4. So that means X was a second order reaction with respect to X. The order of the reaction would be second order. But when it comes to Y, order of the reaction with respect to Y is going to be 1. But you have to show that while after calculating, after carrying out a calculation. So for test 2, we'll write an expression, right? Rate was, when it comes to test 2, the rate was 4.0 into 10 to the power minus 2. We'll leave out the units for this one, and the rate constant was there. Apart from that, concentration of X was 0.5 moles per decimeters cube, and we had M, which is the order of the reaction with respect to X. And then we have N, which is 0.25. So the concentration of Y actually 0.25. So this is our expression 1. And for test 3, we see that the rate, for test 3, the rate is 8.0, concentration of Y is 0.5, while the X concentration has remained the same. So rate was 8.0 into 10 to the power minus 2. Rate constant was still there, we don't know it. And the concentration of X was not changed. And concentration of Y was doubled, 0.50. And let's call this expression number 2. Again, the expression number 2 has larger values, so we will divide 2 by 1. So at that point, you'll get 8.0 into 10 to the power minus 2 divided by 4.0 into 10 to the power minus 2 equals to K 0.5 to the power M 0.5 to the power N divided by K. The concentration of X didn't change, right? 0.5 to the power M still remains. Now in this reaction, we didn't change the concentration of X, but the concentration of Y was changed. So in this case, we saw the expression 2, concentration is 0.5. Expression 1, concentration of Y was 0.25. You can see that these cancel off along with these K values and these 10 to the power figures. And 8 divided by 4 is going to be 2. That is equal to, we can see over here, 0.5 divided by 0.25 to the power N. So students, when you divide these two, the answer would be 2 equals 2 to the power N. So what should be the value of N? You know, 2 to the power 1 is 2 itself, and 2 to the power N is written over here. So therefore, we can find out the value of N, that is N equals 1. Now we predicted this just by looking at the data that we had on the table. So we can write down order of the reaction. Order of reaction. With respect to Y equals 1. So order of the reaction with respect to X was 2. Order of the reaction with respect to Y is 1. Write an expression for the rate of the reaction. So rate of reaction is equal to rate constant, concentration of X to the power M, concentration of Y to the power N. Now we have no need to have these arbitrary M and N included here, because we already know the order of the reaction with respect to each reactant. So we can write the correct rate expression. Concentration of X to the power 2 and Y concentration to the power 1. We don't need to include the 1. We can leave it at that. So this is the answer for this question. Rate is equal to rate constant multiplied by concentration of x raised to the power 2 multiplied by concentration of y raised to the power 1. So this is going to be the answer for this part of the question. Calculate the rate constant. Include the rate units. Now students, we know everything that is there to know about this rate expression. We know the orders, we know the rates that are given in the table, we know the concentrations of each of these reactants. So we can pick one test, right? We can pick one test we like, right? And then we can calculate the rate constant, because rate constant only changes with temperature. So if you keep the temperature a constant, the rate constant does not change. So therefore, if you substitute each of these values into the rate expression that we just wrote, right? We have here the first test, we'll say 0.25, 0.25 and 1. If you substitute each of these values into the rate expression, then we can find the rate constant. Instead of writing m here, we can just directly write the order of the reaction with respect to x, and y is going to be 1. So we know rate, we know x concentration, we know y concentration. Only thing we don't know is k. So if you wish, you can actually rearrange the equation like so. So r is equal to, actually k is equal to r divided by x concentration to the power 2 and y concentration to the power 1. So in this case, the rate was 1.0 into 10 to the power minus 2, and x concentration was 0.25, multiplied by y concentration also in this particular test, test 1, was 0.25, right? So we haven't substituted the units here. We can calculate the units separately as well. So in this case, if you solve these values, you will get to the final answer. So let's write the final answer here. 0.64. 0.64. Now, in the particular way that I did it, I have not included the units here. Usually you can include the units here in itself, but since I haven't included the units here, we can talk about the units separately. So for rate constant, the equation was rate divided by the concentration of x to the power 2 and concentration of y to the power 1. So rate was given in moles per decimeters cube per second. This was the unit that the rate was given in. And each concentration, now you can see there are concentration of x to the power 2. So therefore, you will have mol dm minus 3 over here taken to the power 2 just for excess concentration. And then when you are talking about the y concentration, again, you have the same unit, moles per decimeters cube, written here. So you can see very clearly moles per decimeters cube here and moles per decimeters cube here cancels off, leaving behind per second here. So the moles per decimeters cube to the power 2 can go up there. So before we do that, we can actually write down this as mol to the power 2 and dm minus 6 as the unit that you see as in the denominator. When you bring it up, the values are going to be mol minus 2 and dm minus 6. Actually, minus 6 becomes plus 6 when you bring it above the line, and per second will also be there. So if you want to rearrange in a way that the dm or positive ones come to the front, you can do so. Not a must, but you can do so. So we can write dm6 mol minus 2 per second. So this is the unit of the rate constant. So you can write the final rate constant as k is equal to 0.64 dm6 mol minus 2 per second. This will be the answer to the question that is asked here. Now, let's move on to the next question. If the concentration of X and Y is 0.08 moles per decimeters cube, calculate the initial rate of the reaction. So, now we know the rate expression. K, X to the power 2 and Y to the power 1. And we know the rate constant as well. So if you know all of these rate constant, X's concentration and Y's concentration, then you can find out R, or the rate. So this value is 0.64. We know the units are dm6 mol minus 2 per second. I will substitute the units here so that you can see how they cancel off. And the concentration of X is 0.8 moles per decimeters cube to the power 2 multiplied by 0.8 moles per decimeters cube. So you know that moles per decimeters cube to the power 2, and this section of our rate constant unit will cancel off later down the line. So we'll observe that in a second. Over here, 0.64. Actually, if you want, we can cancel them off now itself. We know that these cancel off because after we open the brackets, we know this becomes moles to the power 2 and dm minus 6. So dm plus 6 and dm minus 6 will cancel off. Moles to the power 2 will cancel off with mol minus 2. So we still have this to be multiplied. So 0.8 into 0.8 is going to be 0.64 multiplied by 0.8. So this will lead to the final rate, and the unit is going to still be mole per decimeters cube, and we still have the per second part of the unit as well, so therefore per second. So the answer is 0.3276. But we can round it off to 0.328 as well. So the units are moles per decimeters cube per second. This is going to be the rate. And you can round it off to 0.33 as well if you want to keep it to 2 decimal places. So now let's move on to the next question. The table below shows the data collected from a series of reactions that were carried out between reactants Y and X at 360 degrees Kelvin. And then we are asked to find the order of the reaction. So when we are asked to find the order of the reaction, we have to find both the order of the reaction with respect to X and order of the reaction with respect to Y. So students, we already know how to do this. So let's go ahead and do this. So we can write a rate expression. Rate is equal to rate constant multiplied by the concentration of X to the power m, which is the order of reaction with respect to x, and concentration of y multiplied by n, which is the order of the reaction with respect to y. So when you are talking about this particular reaction, you can see we have carried out different sets of reaction, and in certain reactions we can see the concentration of x was kept a constant while changing the concentration of y, and in certain reactions concentration of y was kept a constant while changing the concentration of x. So using these types of reactions we can find out the order of the reaction with respect to x and y. So let's try and find the order of the reaction with respect to x. So let's find out m, that is the order of the reaction with respect to x. So let's consider two tests or two reactions that are done here that will help us do that. So if you're trying to find out m, we need to only vary the concentration of x while keeping the concentrations of y a constant. So we have over here very clearly the y concentration being the same here. So if you take a look at, this is reaction test number 1, 2, 3, 4 and 5. When it comes to test number 3 and 4, we have kept the y concentrations a constant while changing the x concentrations. So we'll write an expression for test number 3 and 4. So in the test number 3, the rate would be 4.064. Rate is 4.064. I'm substituting values for this to this equation. We don't know the rate constant. X's concentration is 0.4 to the power m, and y's concentration is 0.6 to the power n. So that is our expression 1. And for the test 4 that is done, we can write another expression. So for the expression for the test 4, the expression would be 0.16, which is the rate multiplied by rate constant, and the concentration of x has been 0.2 and the concentration of y has not changed. That is our expression 2. So in this case the rate is larger in expression 1, so we'll say expression 1 is divided by expression 2. So when you do that, we can write the equation 4.064 divided by 1.016 is equal to rate constants and for the top equation we have 0.40 multiplied by 0.60 to the power n. Over here we have 0.20 multiplied by 0.60 to the power n. And like we did in the previous question, you can see since the concentration of y was kept a constant, those two concentration values cancel off. This x, this actually not x, the rate constants cancel off. And if you observe here, 1.064 multiplied by 4 would get us to this value. So therefore, the value over here is 4 when you solve it. So 4 is equal to 0.40 divided by 0.20 to the power m. So when you solve this, that is 4 is equal to 2 to the power n, because you know 0.20 and 40, when they cancel off, the value is going to be 2. And 4 can be written as 2 to the power 2. and that is equal to 2 to the power n here. So when the bases are the same, we can say the powers are equal to one another. So n is equal to 2. Answer is 2. Actually, it is not n here that we should substitute, it's m. So let me correct that, because we are trying to find m here. So in each of these places, what you have is not n, what you have is m. So m value is equal to 2. So m was basically the order of the reaction with respect to x. So we can write order of reaction with respect to x is equal to 2. That's just one order out of the way. We have to now find out the order of the reaction with respect to y. We can see here there are certain reactions where the order of or where the concentration of y is changed while x is kept a constant. So for example, if you take these two reactions, you can see x concentrations remain the same while the y concentrations are changing, and when that happens, you can see the rate of the reaction has changed. So let's focus on those two reactions, that is reaction number 3 and reaction number 5. That's reaction number 3 and reaction number 5. We can also use, if you want, you can use reaction number 2 and reaction number 4 as well. Those will also get you to the answers. So we know already the concentrations of reaction number 3. When it comes to reaction number 5, we need to include them in our expression. So we have already written an expression for reaction number 3, that is here. We'll write another expression here when you are calculating n, and that expression is for the test number 5. So the rate is 0.058, 0.508, not 058, 508 is the rate, is equal to rate constant multiplied by concentration of x. Concentration of x is 0.04, concentration of y is concentration of x is 0.4 and concentration of y is 0.3. So we'll call this expression number 3. So we have already written an expression for the test 3 that we are interested in, right? Test 3 expression is this. So that is expression number 1. So if you take expression number 1, which has a larger rate, and divide by expression number 3 that we just wrote here, we can get the rate for our get the order of the reaction with respect to our reactant y. So 4.064 was the rate of the test 3. For test 5 it was 0.508. Then we have the K value here, and excess concentration in both cases are 0.4. Y's concentration over here happens to be 0.6, right? 0.6. And when it comes to expression 3, x's concentration was 0.4 to the power m. We haven't changed it, and the y's concentration is 0.3. You can very clearly see at this point that these k values will cancel off, x's concentration values cancel off, and when you try to find out what has happened over here, so the increase that you see here is 8 times. So if you multiply this by 8, it is going to be 4.064. So let's cancel them out. This is going to be 8. This is going to be 8. So the answer here is 8 is equal to 0.6 divided by 0.3 to the power n. So this is the order of the reaction with respect to y. The n represents that. And when you solve this, the value that you get is 2. So that means 8 is equal to 2 to the power n. Now we have to find out the value of n. And the base over here has a value of 2 in this exponential expression. So we have to write 8 as a power of 2. And we can write 8 as a power of 2 in order to get the answer. 2 to the power 3 is also equal to 8. So we can write that like so. So when you do that, we can really find the answer for n here. Since the bases are the same, the powers will be equal to one another. N is equal to 3. Meaning, order of reaction. Order of the reaction with respect to y happens to be 3. Order of the reaction with respect to y happens to be 3. Now students, they are asking for the overall order of the reaction, right? So just to clarify, we write the rate expression. Rate is equal to rate constant multiplied by concentration of x, and the order of the reaction with respect to x happens to be 2. We calculated that, and the order of the reaction with respect to y is 3. So the overall order of the reaction, order of the reaction is equal to the orders of each reactant added together. So we have 2 plus 3, which happens to be 5. So the answer to the question that is asked is the overall order of the reaction, in this case, is 5. So now let's move on to the next question. When the concentration of X is 0.3 moles per decimeters cube and the concentration of Y is 0.4 moles per decimeters cube, find the initial rate of the decline in X concentration. So now they have given us the concentrations of both reactants. Now students, in this question, they don't ask us to find the rate constant. They have only given us the concentrations of each reactant and asked us to find the initial rate. So do we need to find the rate constant to get to the answer here? The answer would be no. So if we assume that this reaction is done in the same temperature, because even if that information is not given, we will not be able to answer the question if this reaction has been done at a different temperature, because as you change the temperature, the rate constant will change. So we have to assume, that is an assumption that should be made. So if this reaction is done at a different temperature with the given information, you can't predict the rate constant. So we assume that this reaction is done in the same temperature. So using that, we can find the rate of this reaction. But even to find the rate of the reaction, we do not need to find the rate constant, Because we can write an expression for this particular rate. Let's say the rate of this reaction is equal to R, and that is equal to rate constant multiplied by X concentration. Now X concentration is 0.3, and we know the order of the reaction with respect to X, which happens to be 2. And we also know the Y concentration, which happens to be 0.4, and we know the order of the reaction with respect to Y. So this is an expression we can write for the given information. So they have given this information and asked us a question. So only things that we don't know is rate and rate constant. In a similar way, we can write an expression for one of the tests that were carried out and then divide the two. So when you divide the two, only thing that we don't know in both of the expressions are going to be the rate constant. They will cancel off, leaving the only unknown, which is the rate here. So we will take one of the tests that they have done here. That will make it easier for us to answer this question. So let's move on to the question we were doing. I believe this is the question. So yes, right? Okay. So the initial concentration of X that they have given us is 0.3, and the initial concentration of Y they have given us is 0.4. So we can take something like this concentration, right? We'll go with either one, it doesn't matter at this point. So we can take either the first or the second reaction. So we will take the second one, right? You can choose whichever one you like, because in each case they have given us all of the information that we need. So over here 0.127, 0.20 and 0.30. So to write that expression, we can write for the test 2, the rate was 0.127 is equal to rate constant multiplied by concentration of X, which happens to be 0.2, and concentration of Y. Concentration of Y is going to be 0.3. So this is the second expression we can write here. In both of these expressions, we have only one unknown that is common to both of these expressions, that is X, right? So we can see the values that we have for the expression 1 are larger. So we will go with 1 divided by 2. So expression number 1 divided by expression number 2 will give us this value. R divided by 0.127 is equal to, you can see that the k's are cancelling off. We'll write that down here. Rate constants k will cancel off, and we have 0.3 to the power 2 multiplied by 0.4 to the power 3. Over here we have 0.2 to the power 2 multiplied by 0.3 to the power 3. You can very clearly see these cancel off, leaving behind the rest of the expression. So R can be written as 0.127 multiplied by 0.3 divided by 0.2 to the power 2 0.4 divided by 0.3 to the power 3. So when you solve this, you can get to your answer. So you can write this as 3/2 and 4/3 and then carry out the calculation as well. So let's move on ahead and solve this equation. So we can write this as 0.127. We can write these values as 3 divided by 2 to the power 2 in a more familiar form, because when you simplify this, it's going to be 3 divided by 2 and 4 divided by 3 to the power 3. So if you open the brackets, you will see this is going to be 0.127 multiplied by 9 divided by 4 multiplied by 4 to the power 3 is going to be 64, and 3 to the power 3 is going to be 27. We can very clearly see 4 and 64 cancel off, leaving 16 behind. 9 and 27 cancel off, leaving 3 behind. And then we can solve this equation when you multiply 0.127 by 16 and divide by 3. You will get to an answer like 0.677. And we do need to know the units of this as well. Now keep in mind over here for this particular part, and when it comes to carrying out this calculation anyway, the unit of this reaction rate should come in moles per decimeters cube. So when you substitute these values, you can write moles per decimeters cube per second, because this is going to be the unit of this reaction rate. Reaction rate always comes in moles per decimeters cube per second. So in each of these substitution steps, writing that would be helpful. So finally, the answer that you get is going to be coming in this unit. So unit of the reaction that we take initially, the test 3, or in this case we took one reaction from the table that was given to us. The rate unit of the rate of that reaction was also moles per decimeters cube per second, and this reaction is no different. The rate of this reaction should also be communicated in the same unit. So the answer is 0.677 moles per decimeters cube, moles per decimeters cube per second. So this is how you would find the rate of the reaction without finding the rate constant of this particular reaction. We have written the expression. We know that there is a rate constant, but we didn't have the need to find the rate constant because the question doesn't ask us to find the rate constant. At that point, students, if they don't ask us to find the rate constant, there are ways of getting to the answer without calculating the rate constant. So you can just write two expressions as we have done here, and then directly move on to finding the reaction rate when the concentrations of each reactants are given. So students, with this we can conclude the question discussion. In this part of our experiment, we have looked at how to answer questions that are revolving around calculating the rate of reactions, writing the rate expression, finding the rate constant, and we also saw how to answer questions revolving around what happens when we increase the temperature of one reaction mixture while keeping the temperature of one the same. So we were able to answer what happens when we provide more energy to one system, how the rate changes, and what factors influence the increase of the rate at a higher temperature. So students, by now I hope you have a good enough understanding about the theory parts and the practical that is revolving around experiment number 31. So now we will conclude this experiment and we will meet you again in the next experiment.